And there's more that I wanting to join the Zoom.
Like a mic have just big. I think we're calling us up and asking remote folks. I think
I think we'll start with that and see. Could you monitor on Zoom to see if they are, as we go, if they can everything can you hear it?
Okay, I'm going to take Nick back with me to grab some more power sources for you guys. It looks like you guys are really short on some extension cords. And then he's here until 12 o'clock.
Thank you so much. Yeah, you're very welcome. Thank you.
Need to be admitted again. I need to be admitted into the room again. That's weird. I thought I'm a purple today. Maybe my co-host identity. Yeah, I think it is.
No.
Hold on.
All right. All right, everybody, made it. Thank you so much. It's very good to see so many seismologists in the room. Yeah, it feels like it's gonna be a really good week. And thank you for traveling here and bringing the sun. We always like that in Seattle. And we are bringing to you research grade software. And we're gonna teach you about our own software through the SCOPED and QuickWatch project. But really what this is about is starting to reach out to this community of great scientists that might use and help us develop this software and work together to really advance and accelerate science. And so I welcome you to Seattle, which has some of the biggest data sets in the country on campus. I wanted to tell you that the SCOPED project that is funding this workshop is actually gathering a lot more efforts that have been fueling the software development of that we have in this project. And so we have the SCOPED logo shown here, main institution, University of Alaska Fairbanks, Texas Advanced Computing Center, Lamont, Columbia University, UW, Colorado School of Mines, UC San Diego is very well represented as well here, instructor and participant. And a lot of that is also underpinned by these massive cyber infrastructure projects that are supported both at the NSF level, but also in Europe. And so what we're trying to show you is the breadth of really advanced computing for seismology, both in the numerical simulation work and also the big data analysis. But we are, it's the first event really at that scale. So we're hoping for a lot of mutual interactions to tell us how to improve, what to modify, how to better teach, and hopefully you would be enticed in using our software for your own research. But please bring your ideas because a good software comes with many diverse minds. So a little bit of logistics for today is we're going to be using Zoom for screen sharing, for recording. If you happen that you'd rather Zoom from your hotel room, that's also okay, but please join us in person if you can. We use Slack extensively for debugging. In person, I'd love to have questions, spontaneous questions, and raise your hands and please ask because that's the benefit of being all together. But for kind of longevity of these questions, feel free to use Slack and we'll be monitoring this today, but also in the coming months. And so it's a nice way to record your questions, your debugging. We can share that to more users and more participants who are actually on Zoom as well. We may recommend that you use the reply to the thread, replied in thread way to communicate, to organize the discussion. I love organization, so you'll see my style. And it really helps us, be efficient at communicating. So what else? We have a code of conduct, which is listed on this sheet. These Google slides, I think, are linked on the website. So please look at it. We do ask that everybody is being polite. We're very international, very diverse, and we're just going to respect all of our differences and in a collegial way. But I'm convinced that this will happen. Okay. So next, I wanted to bring a bit about what I personally am super excited about in the coming few years is the fact that we have potential all of these seismic data, 20 years of continuous seismic data that is stored at the EarthScope data services. And you can see that all of the data that is collected on isolated islands in continents, in subduction zone, in transform faults in the middle of the continent, all of that data is going to be accessible in a cloud infrastructure. What really inspires me from this is the idea that we can do really large-scale computing with consistent, similar workflows. We'll be able to be uniform in our scanning of the data in a way that was not possible before that. This is about a petabyte, less than a petabyte of data, which actually for other research fields is modest, but it's not something that you would have been able to process until this is to the cloud. So what really inspires us, I think, is looking at this big data seismology grand challenges. This is my personal perspective. I'm very interested in thinking about whether or not the Earth structure is stationary over time. And with 20 years of continuous data, I think we'll be able to unravel temporal changes in the Earth structure at really global scale and with really high spatial resolution. We'll be able maybe to do some data discovery, aided maybe by machine learning, by scanning these petabytes of data. And especially with distributed acoustic sensing, I think we are able to see new phenomena that we were not able to really tease out of the conventional seismometers. And so maybe we can gain a new scientific understanding in seismology and its frontier. Other great challenges that I think DAS may also bring us is once we can process DAS maybe on the cloud or elsewhere, it's going beyond seismology. I think there's a lot of potential for using our methodologies and our ways to scan the data, but to also explore other things in the ocean, in non-earthquake geohazard phenomena like landslides, thinking about tsunami genesis, and there's a great potential for also doing oceanography, but using our seismology methodologies. What we're going to show you today is potential methods that may allow you to really scan data at the billion scale. So this is a work that was led by in Felix group that was able to look at millions of small events and moderate size events in Italy. And what you can see from this is actually still one of my favorite photos for a figure for a very accurate earthquake catalog, is you can see the millions of earthquakes in a map view, but then you do cross-section and you can start seeing the complexity of fault networks by using these the techniques that they've been using, which is machine learning aided for phase peaking. So I think this is the kind of scientific discovery that will be fueled by advanced methodologies and availability of accessibility of data. Yeah, so I think they found these are the 1.5 million aftershocks, which is kind of like, anyway, these are the scale that we'll be able to do big data seismology. Today, there is on the cloud maybe 200 terabytes of seismic data from 2 regional seismic networks in the same state. In Southern California, you have on the cloud the SCEDC dataset, 20 years of continuous seismic data. The Northern California just moved on the cloud a couple of months ago, different region, but we can still play with it this week, which also has, hundreds of channels in similarly 20 years worth of data. And so one thing that I'm very interested in doing in the near future is whether or not we can do a massive cross-correlation of all of these sensors to try to understand temporal change, static Earth structure at multiple scale, but also temporal changes in the Earth over the past 20 years. And so some of the examples of really doing multi-scale imaging is, what if we could integrate some distributed acoustic sensing data in the urban setting? This is an example where we are here, and there's a fiber that goes from this campus to the next. And so the uni has cross-coded in the room here, cross-coded all the DAS data that we have, and we'll be able to do really fine scale imaging. You have also an image of basin scale structure from using nodal data in Southern California, and near surface environment critical zone type scales using distributed sensing. So I feel like we have huge opportunity to do multi-scale Earth imaging. So I just wanted to go through an introduction of the team for today. And this is my motivation. Now let's talk about the team. We have many instructors. I think we're about 20. And we have graduate students and postdocs and faculty who are trying to catch up with the grad students and postdocs. So bear with us there. But what you'll see throughout the week is a pretty beefy, but very interesting, we think, program where a lot of our team members are going to show you their work, and we'll walk through together on these software. And you will be telling us about the bugs and things that you'll see to improve. So here I am. I'm just going to introduce myself. Marine Denol. I did my PhD at Stanford. I did a postdoc at Scripps, a little bit with Peter. I started at Harvard in 2016, and then I moved here in 2021. I wanted to tell you my coding path. A lot of it was self-taught. I was a geophysics PhD student. I learned a lot of Fortran, shell scripting there, maybe some MATLAB. And so that was my foundation. During the postdoc, I started automating things in MATLAB. And then as a prof, the time you have so much time, free time to learn how to do your own things, I learned Python and Julia the hard way, meaning I just had to do it. And also I was trying to work with students. And so my path to coding is self-taught, which is not the best practices. But we have great students and postdocs to teach us how to do this. In terms of interest in seismology, I'm really fascinated right now by probing seismic events, but whether or not they're earthquakes, non-earthquakes, and really the dynamics of the near-surface environment. In Seattle, you will see a volcano. I hope you get to see Rainier. I think you'll see this week. It's pretty massive. It's got a glacier on top, a couple of glaciers on top of it. Landslides, avalanches, earthquakes, volcanic system. It's my little gem right now because we have everything is mixed up together, and I'm just having a lot of fun trying to decipher what these are. Also, we sit at a very close to a seismic network, and so actually Renata Hardrock in the back is a network manager. So we have a ton of data and experts on the data that can tell us about this is an instrument glitch. Don't interpret this data. And so it's been really fun to move this way. I will be leading a couple of tutorials, the CLAD 101, co-leading with others, our Noise Spy project, and maybe some machine learning at the end of the week. Some highlights on my research, looking at avalanche in Mount Rainier, some DAS data that we're collecting, and getting to the farm, as you can see on the top right, where I went on the field and collecting some DAS in the farm to look at soil science. All right. Who's next? Ian.
How is this going to work?
You just come here and
around, get a stage. Okay,
go for it.
go for it.
Mhm.
Okay. Well, so my name is Ian. I'm one of the SCOPED co-PI here and helped Marine organizing the event. And I'll be mostly giving the tutorial instructions on HPC related topics and a bit of data management tools for open science related topics. So I got my PhD from Indiana University a while back. And yeah, my career path is a little bit unique in the sense that I'm by training a seismologist, but then I got into this HPC research stuff. And now I'm actually working at the Texas Advanced Computing Center doing seismology plus high performance computing. So my code path, so pretty much my PhD work are mostly in C++. That's also because I'm working with Gary Pavlis, who's also the instructor here today. He's a really C++ geeky person, but then, during the process, I also had to pick up Python and MATLAB and others since they are also popular to the seismology community. And for my postdoc, I started doing some really low-level research into high-performance computing, where I developed a parallel runtime system. So it's really an enabler for your HPC code to run efficiently on HPC clusters. Yeah, and now I'm just doing everything, seismology, HPC, using all this code. So yeah, also the third section is interested in seismology, but my interest is in seismology and HPC, so I guess that kind of counts. So I did, signal processing and receiver function for my master, and my PhD work is actually using the 3D plane wave migration code that Gary wrote, and we did high resolution imaging of the 410 and 660 discontinuity, and we look at the water in the mantle transition zoom and all that good stuff. And now my main project is actually developing seismic data management tools. And also I have other HPC related projects, like building the machine learning framework and doing a profiler for the HPC systems, which you can see some details here. So really those are the three projects that's ongoing. Well, I guess the diamond one is particularly interesting. It's actually building a community gateway for training large neural network for the science, for different science domains, actually. So, I'm actually going to be interested looking into, applications of seismology into this framework. So just come talk to me if you are interested in any of that. Thank you.
Thank you, Ian. Yeah. Bryant. You'll be called, so be ready.
Morning, everybody. My name is Brian Chow. I'm an assistant professor at University of Alaska Fairbanks. My path was I did a master's at LMU Munich with Heiner Eagle. So that was kind of when Ops 5 was being, I guess, matured there. And so I got a really nice start there, being introduced to Python as a use for seismology. And then I did my PhD at the Victoria University of Wellington in New Zealand, doing adjoint tomography. So doing a lot of SPECFEM simulations and inversions. My interest in kind of computation also came in through the development of workflow tools. As many of you know, inversions can be really computationally, but also algorithmically expensive. And so I didn't really want to spend all my time sitting on a supercomputer and like manually running jobs. So I devoted a lot of energy into automating things and writing kind of Python packages in order to make things a little bit easier for people to do adjoint tomography, full waveform inversion. Then I went to University of Alaska Fairbanks for a postdoctoral fellowship, also doing adjoint tomography and improving those workflow tools. And now I'm a professor trying to formalize this a little bit more. And today or tomorrow, I'm going to teach you about SPECFEM for the morning session.
Thank you, Bryant. Well, Carl.
Hi, everyone. I'm Carl. I'm one of the one of the 5 PIs, and I don't think I'll read through all this, but yeah, interest in seismology. I'm from Alaska. I've always felt earthquakes, and maybe these are the things like, how do we find ourselves where we are? So during my master's, I went from a liberal arts college with very limited computing, thrown into this master's degree with John Woodhouse, who had Fortran 77, no implicit variable declaration. So that's what I thought computer programming was. And it was a nightmare. So at the same time, I took this scientific computing course by Nick Trefethen, who I think was the first MATLAB license ever. He had a little plaque from 1982 that said first license. So I had these two extremes of coding. And then, yeah, I saw these papers during that time on the SPECFEM and sort of just, for me, I couldn't believe that this is possible. So some of you might come into a field where you just can't believe this can be possible to simulate the whole wave field in a really HPC setting. And so that was 22 years ago. And those are the tools that we'll be featuring today. So I think I put one slide after this. Just I'm really into sedimentary basins and just the fact these are simulations from 2 parts of Alaska, Cook Inlet. If you were at SSA, there's Anchorage on the right, but just the idea that all these detailed structures are interested both for ground motion amplification and the structure of these sedimentary basins, what we can learn about. A lot of them have oil and gas, things like that. So yeah, Yuan Tian is a postdoc who's now at Lawrence Livermore National Lab working on SCOPED. Well, he's still working on SCOPED related science. So yeah, that's it. So I'm really excited that this workshop is being pulled off. I feel like even at this stage, we should still give Maureen a round of
No.
applause before too long. Yeah.
Before you realize.
Yeah.
Thank you,
Thank
Carol. Felix.
I keep this short too. I did my PhD in Zurich, ETH, and then I moved to Menlo Park for a postdoc, and then went to London, Columbia, the rest of my career so far. Mostly self-taught computing, programming. Anybody knows Fortran? Oh, good. Fortran and MATLAB and lots of shell scripting. Mainly because Python is too slow. Anyway.
Still true.
So right now I'm an earthquake seismologist, I would say, but my PhD was in geophysics and active source seismology. But those two are very complementary, so it's actually it was a good change. I'm mostly interested in looking at seismogenic structures and then what we can learn from high precision earthquake locations. And so as this course will be, it's about maybe next one. It's about producing those very large catalogs that Maureen was showing an example of from central Italy. But I think my main message here is that it's not about building huge catalogs. It's about understanding why you want to build those catalogs and the science you want to address that. So I'm showing 3 examples that we are currently working on and the research topics. So in Northern California, for example, we get a resolution where we can resolve repeating earthquakes at a scale of tens of meters on the left side. And then we can use those repeating earthquakes to estimate the slip on faults and image slip across state boundaries. In central Italy, which is one of the example data sets that we work on Thursday, that's the data set that Maureen was showing, where we can image faults at seismogenic depth on the lower right. So Maureen showed dots for the hypercenters, but when we actually plot the density of either number of events or moment, then we see a very sharp structure. This is a normal fault that's truncated at the base with what we think is a bookshelf system that's at the intersection. And then we get the fault geometry, which is worked before what Carl and Egru are doing in terms of resolving moment tensors and so on. And then the third one is an axial CMAT volcanic system with OBSs and working with Taiwan as we see here too. Oh yeah, by the way, repeating earthquake work with those working Teresa, we here too, talking on Friday. So axial CMAT is Taiwan, so we're working on a data set that is very rich in terms of the diversity of earthquake sources and find recursory signals with unsupervised. So those are all the tools, but again, most importantly, when you build those catalogs, you need to know what you're looking for.
Thank you. Great, thank you so much. Kaiwen, would you like to?
Hi, I'm Carla, and I'm a postdoc working with Linux, and I did my PhD at Stanford, and then afterward I went to Lamont at Columbia for my postdoc. So I'm mostly coding with MATLAB and Python, and as just mentioned, like we do build a large scale earthquake catalog, and we also use unsupervised machine learning to learn and hidden patterns in the earthquake catalog we built. And also during my PhD, I also work with works on the induced earthquakes and also the analog seismogram. So we use machine learning tools to read those old film-based or paper-based seismograms and extract information from them, and trying to make this process more efficient by introducing image-based processing rather than like a human analyst speaking manually. Yeah, that's it.
Thank you so much.
Hi, I'm Teresa Sowie.
I did my PhD at Vermont Doherty Earth Observatory, where I'm at Felix and Taiwan. I'm actually currently a mental health postdoc at the USGS at Moffett Field. I like many here, I'm also kind of self-taught, but I'd like to give a shout out to Stack Exchange, and more recently ChatGPT. And so my interest in seismology and my focus for this week is unsupervised machine learning for seismology. And so kind of like Felix brought up, when you have hundreds of thousands or even over 1 million data points about earthquakes, how do you get a broad understanding of the families, the groups of events in there without using things like cross correlation or template matching or labeled data sets? And so that's the kind of questions that we'll be approaching this week.
Okay. Thank you, Teresa. Yeah.
Welcome everyone.
It's not as well set up as SSA.
So I'm one of the 5 SCOPED PIs. I'm a postdoc from Colorado School of Mines. So I did my PhD in 2009 at Berkeley in global seismology. Then I was a postdoc researcher at Princeton. I spent some time there, mainly focusing on global scale for waveform inversion. And then I moved to a faculty position at the University of Bordeaux in southern France, because Paris was nice, but it was too nice. Then I decided to come to the US, Colorado. And now actually, currently I'm on sabbatical at ETH Zurich. So if I make anything stupid, it's because of my jet lag. And so my coding learning path is kind of similar to the other PIs. It's mainly subtle. And probably it wasn't a very conscious decision. I remember at some point during my PhD, I told my supervisor, thanks to Jano, I told him that maybe I need to take some courses, programming courses or HPC courses, numerical methods. And the answer I received was like, learn it yourself. You have to learn how to teach yourself. And I think this is probably one skill that you need to develop during your PhD if you would like to stay in research. And mainly, actually, I'm probably one of the first users of Stefan 3D Globe package. And I learned most of the things when I was trying to read and understand something in the code. So nowadays we have lots of community codes, open source codes. I strongly recommend you to dive into those codes and follow, try to understand what this is one of the ways that I found really helpful. So during my master's, I used MATLAB, and during my PhD, I upgraded to Fortran 77 for similar reasons to Carl. That I had codes from John Woodhouse and John Franker in Fortran 77. Then Fortran 90 was really great for me. And now I'm using whatever I need to use. I'm a global, primarily I'm a global seismologist, interested in imaging deep earth, mantle and the core structure. However, I have interest in multi-scale wave simulations, seismic wave simulations, and full waveform inversion that it's not scale limited. So seismic tomography, passive source, full waveform inversion, seismic hazard assessment. But one thing that I would like to highlight, in addition to what Felix and Marie highlighted, data is one component of the problem. And what we are trying to do together with similar to the Alaska group, we are trying to take the full physics, or not full physics, but the full complexity of the wave propagation into account when we are imaging Earth's interior. And this is then the problem has 2 legs: high performance computing and big data. And how can we harmoniously combine them together? It's one of the main challenges right now in seismology, and this is also one of the main goals of the SCOPED project. So welcome everyone. Oh, so I need to continue. Oh,
Sorry.
so I actually summarize the types of research we do at School of Mines. So
from global scale to continental scale, and even recently, these are the full waveform inversion results. So from the Middle East and global scale, and that's we are interested in multi-parameter inversions. Like right now we started trying to address the anisotropy in the mantle, or trying to address the attenuation structure. But our interest is not limited to deep structure. We are also interested in multi-parameters, so like trying to use DAS. You see an example of data we collected using the telecom cables in Istanbul last February. And surprisingly enough, when we were demonstrating this cable, if we could get some meaningful signals together with the Zurich group, Andreas Fiedner's group, and the Candil Observatory, we recorded, by chance, coincidentally, we recorded these big earthquakes, East Anatolian earthquakes, magnitude 7.6. This is one of those records. So the question is, how can we, as a global seismologist, as a skilled seismologist, I can always complain about the amount of data, which is never enough. So that's why the way to go is to try to combine different data sets from broadband stations, from DAS, or from mermaids. Especially we have ocean bottom seismometers. As a global seismologist, we have lack of data from oceans. But then the question becomes, how are we going to harmoniously put them together to be able to get something meaningful out of that? So these are all kinds of research questions. And our research is not limited to Earth. You see one wave propagation simulation from Mars. We can also use these numerical simulations to reach other planetary bodies, especially if there is strong political variations, which forces us to use numerical simulations. Thank you.
Read them.
This one
Is online maybe. If you're here, can you unmute yourself?
Okay, can you hear me? I'm unmuted.
Yeah, the sound.
Hello?
Yeah. Perfect.
Hello,
Yes.
I am Ridwan. Again, I am self-taught in programming as well. So I learned Python in high school, and then I lucked out because it's such widely used right now in seismology. Then during my master's, I learned Fortran, and then when I started my PhD with Ebru, I had to really learn parallel computing and big data stuff and high performance computing. And I'm currently working with Ebru for global and regional full waveform inversion and seismic tomography.
Thank you so much. Masaru, are you
hello.
around? Yep.
Yeah. My name is Masaru Nagaso. I'm another postdoc working with Ebru. I've just joined this team from this January. So my code learning path is like this. So the first time when I touched the coding is just for my bachelor's degrees, final research program, which was with C and MPI for running the code of fracture mechanism on some small size clusters. And after I started to run C++ and C# and OpenMP and OpenGL just for visualizing the result during my master's research project. Then in the PhD, I started to use Fortran and CUDA and Python for my PhD research, which was with SpecFM 3D or 2D. So I was studying with Dmitry Komatic, who is the developer of the SpecFMs. And thereafter, in my postdoc, I ran C++ and MPI with shared memory and something like that, just for the optimization of the code for HPC systems. So, and some other techniques was necessary for just earning some money to live. So my interest in seismology is to optimize the code for HPC systems like using MPI, GPGPU, or OpenMP, and SIMD optimization. And IO optimization is what I'm now interested in. So thank you very much.
So hello everyone, I'm Arun Bush. I am a PhD student at Colorado School of Mines. I did my bachelor's and master's in geology in either Kolkata, India. So as most of the new generation students, I am pampered with Python. I also have a little bit of background in C and I understood Fortran to debug and understand spectrum. That's my coding background. And I use numerical wave propagation to understand the effect of rotation and animation and those things on global seismograms, synthetic seismograms. And I'm also trying to do global for inversion, focusing on the animation and analysis. Thank you.
Thank you. Shibin?
I'm Shibin. Before I did my PhD, I had some background in geology, and then I realized I'm more interested in data waveforms. So later I started my PhD by looking at the waveforms to understand earthquake rupture processes. To achieve the goal, I learned C language to write the code for nonlinear inversions. And later, motivated by reviewers of my paper, the reviewer was asking, what about the topography effect of waveforms relations? So I had to learn the Fortran language to run the spectrum. Also, it also helped me to do another project on earthquake cycle simulation, also using Fortran. Later, I got interested in machine learning. So everybody was using Python at that time, but during the last year of my PhD, so I learned PyTorch and TensorFlow using Python. So my selfie was taken. This is my most recent selfie last June, when we were deploying the DAS instrument in Coping Lake in Alaska. And this experience made me feel that seismology is beautiful. So hopefully I can show you some beautiful DAS data on Friday tomorrow.
Yeah,
thank you.
Wanfu?
I'm currently postdoc with Marine, and so my background is I have my PhD and previous degree in Taiwan. So and I forgot to do here. I have to spend 1 year in University of Utah as a postdoc before I came to my school. So my coding learning path is Fortran and C++ during the PhD and master degree, and now mostly Python. Yeah. So my interest in seismology is I'm mostly interested in ambient noise seismology and using ambient noise signals to understand the temporal evolution of near surface structure change and probably change maybe rainfall related or weather related signals to the subsurface change or agitation over time. So yeah, and the thing is that during our school to learn how to use cloud computing, just like we will see in this week. So yes.
Yeah.
Thank you.
Thank you. You?
Hi everyone, my name is Yi. I'm currently a 30-year PhD student at the University of Washington, working with Marine. And yeah, I got my physics background back in China from in 2020, and I joined it up in 2021 at here. And my coding learning path gets started actually way back from the college, and get started with QBasic. Anyone know this kind of language? Oh, QBasic. Oh, Renata. Thank you. Yeah, and later during undergraduate, I did a lot of C and MATLAB coding or plotting with plotting, and later get interested in working simulation. So I'm kind of moved towards Fortran and a lot of trouble with Smith files and Python and things. To be honest, entering the UDA, I kind of moving towards Python.
study, write some code for native data processing. That's currently my work here. Thank you.
Thanks so much. Alice is online.
Hi, can you hear me?
Yes.
Hi, I'm Alice Gabriel. I'm associate professor at Scripps and a guest professor at LMU Munich. I'm not a SCOPE PI, I'm a SCOPE fan, and I'm really happy that that PIs invited me. And I'll be there in person tomorrow and on Wednesday. I have to teach today and couldn't make it. So my career path, I did my PhD at ETH Zurich in 2013, and then went on to be a postdoc in Munich and to become all the way to professor there. And now, since 2 years, or a little bit less than 2 years, I'm in San Diego as an associate professor. So I started coding actually in the late stage of elementary school, I guess, in the US. I don't know if anybody knows about Logo or Turbo Pascal. So that's kind of the start. My kids learn Scratch now, which is much cooler, or Minecraft, but it wasn't that cool. And then I went on to use Fortran 77 and 90 in my master's and my PhD. As a postdoc, I really started with parallel computing. So there's a code that SciSolve used at that point, hybrid OpenMP and MPI, and a mix of Fortran and C for a long time. We're only C++ now, so we kind of changed gears a little bit. As a professor, I'm trying to keep track of a lot of things, including Julia, then also CUDA, SYCL, HIP, OpenCL, all of these new things. But in reality, sadly, it's ramping down in favor of writing proposals and writing papers and teaching. So it's more, but less in depth, I would say. So I'm interested in earthquake physics in all of its flavors. Maybe the next slide has some more examples of that. So these are just a couple of rupture dynamics simulations that we've been doing lately. And I just put those on because this is what the training on Wednesday will be focusing on. So that's a physics-based way how to model dynamic rupture and wave propagation at the same time. And there's some more. I have a website and a Twitter account, and I will be there tomorrow, so you can ask me more. So I just pass it on to Jeremy, I think.
Thank you, Alice.
Hi everyone, I'm Jeremy. I'm a third year PhD student at Scripps, and I'm quite advised with Alice and Wan Yuan. So I did my bachelor in Hong Kong in 2021, and I start with C at the time. They don't have Python class right now at the time, and then I just self-taught myself Python, mostly use Python and the HPC to use the SciSolve. So I'm interested in imaging earthquake kinematics from observations, mostly large earthquakes. So study about fire fault models, multi-CMP methods, and how these observations inform the earthquake source. So we try to understand it and bridging it to the numerical simulations. For example, we use the SciSolve to understand what behind these rupture fronts. And I mostly focus on subsystems on earthquakes. Thank you.
Thank you, Jeremy. Thanks for joining us. Okay. So I think that's kind of it for the introductions. And you can see it's pretty broad. I mean, it's still seismically related, but we are going to be exploring a lot of different science in seismology. I wanted to bring a few more things before we gonna get started on a lecture about open science. I wanted to remind everybody about the website that we've made. Whoops. This is the SciScoped Workshop 2024 website, on which you have an idea of a schedule. And sometimes I have even linked some of the slides, like for this next lecture, it's already on there. And so on this website, you should be able to see updated material, and you can always refer to it when it's updated. If not, we're trying to compose a Jupyter book that is linked there. It's now gathering multiple years actually of effort, because we are running this event in multiple ways. So you can see past events, the data mining workshop we had in SSA, the virtual workshop we had last year, which was entirely virtual for that context. And we're starting to compile some of our tutorials there, at least for the big data part, for ambient noise seismology, the cloud, some of the ML work. So that's going to be the two resources. We have the GitHub page, which is the website, and then the Jupyter book, on which are linked some of our posters and slides and everything. And also we started, so I'm just gonna excuse myself. We have this little sticky notes you see on your thing. Because we're very diverse, here's the legend. I hope that you all have a sticker, not to label yourself, but to identify with one of the research interests. And with the color coding, I like to, I'm interested in too many things. But with the color coding, what you can see them, and you can find your peers that are interested in the same research, and the ones that would not, that would be the new colleagues in different research. And so we'll have lunches where your goal is to match with your peers, with your research friends, and to mismatch so you can get to see what the others want to meet.
Marie, we were batting around which one it should be, and I think I wrote on there your expertise, not your interest, where you want to go. So we had said, put down your expertise. I don't know.
Okay, we can have a different, yeah.
So the point is, I guess, so that we stick with what's written there. Put your expertise, but if you're interested in something that you don't have expertise in, go find those people. So just so we don't get a broken database here. Yeah, maybe put down your expertise. Your closest expertise. You don't have to be that.
Yeah. Okay, cool. There's stickers still there if you have not put your stickies. Next, I want to make sure before I get started on I'm gonna have some water to drink, but do you all have Docker installed? Okay, I want to make sure that since we are sharing a similar Wi-Fi, Docker can be heavy to install. So I want to make sure that you can take the moment now to make sure that Docker is installed on your machine. We can have a short break, Renata. I didn't know there was version context.
This is fine, mostly. But yeah, it would be nice to upgrade to native if you are concerned about it.
But if your computer's old.
Yeah, but if your computer is
Yeah,
old, then,
too old.
then don't upgrade. Yes, I meant to mention that actually. So for those of the in-person participants, make sure you already got your tag account set up. You have a username available, and you have the MFA, multi-factor authentication set up. Because we were actually going to do some practice this afternoon. But before this afternoon, if you have any issues with your account, definitely submit a ticket, because most of the issues is something I cannot resolve. I don't really have that authority, but come to me if there's any issues with your account, and we'll try to look at it together. Okay.
I just wanted to slow down, having a little bit to emphasize that if you've gone to the effort to come here, like when she says, do you have Docker installed or do you have a TAC account, we really have to make sure you have this, otherwise you're not going to get anything out of those modules when they come along. And we don't want to be, we see them coming in right now. Where's the Zoom link for this workshop? There's the TAC account might take some time, might take someone to sort it out. So multi-factor authentication, you have to take a picture of a QR code with Duo, open on your smartphone. Like there's just things to go through. So if you're not set up, just find people. Don't let this just go by with us saying, all right, I'll do it later. Like make sure as we're going through these breaks and everything, Docker, TAC, some stuff, a couple of tutorials will work without anything but a laptop, but other ones, and especially the ones that are kind of exploiting some of these bigger resources like Spec and Flow, we need to have those things set up. Just slow down, reach out to anyone who saw on those slides.
Ready. Awesome.
So I think we need to mute this one and then enable that one.
Okay.
So then it's not going to happen.
Okay, does it work? Can you
For the remote participant, can you let me know if the audio in the room is better now? Because now I'm off the podium. Can you still hear me?
Yeah.
I'm like to the remote. Post in the chat if there's still any issue of the room audio, okay?
Now, you mentioned that it's a peer launch.
Very echoey.
I don't know.
You know, what for the next the talk, maybe we'll do the speaker, and then for the discussion, we'll do the owl.
Sure. Yeah. Let's do that then.
Okay,
Maybe that one.
thank you. All right, back to old school. All right. All right, okay, so what I wanted to start this, please join in the Zoom. I wanted to start this this week by really introducing kind of like the scientific principle behind reproducibility and open science, and as a way to be the root of the way we do science today. And so you may have heard of a few papers that talked about the crisis, the reproducibility crisis. And I'm not sure if you're familiar with this topic, but this is the idea or the data demonstrating that a lot of the publications out there, especially in medical sciences, are not reproducible. And so a lot of the surveys that have been put out show results like this. You can see that people feel that there's a significant crisis. Now, bear in mind, this is the pandemic area, so everything is about a crisis. But it does seem that we are now able to actually look at the papers and their data, maybe their software, and realize that maybe we're not able to reproduce research. And I think as an ethics for us as scientists, the bare minimum is to do correct science. It doesn't have to be always impactful or transformative, but at least we have to demonstrate that we can reproduce what we've done before. And so in this survey, they split between different disciplines to see how much of the surveyed scientists felt like the science was reproducible. And so on the y-axis, you see the percent of published literature that is reproducible or predicted as reproducible. And you can see how the respondents lean toward. So in chemistry, they were pretty confident that a lot of the science was reproducible. In medicine, we're mixed match, and for other fields, we're not. And maybe we have a lot more disparate answers for the earth and in the environment, which is, as we know, very broad. So I wanted to take a few minutes and for you to actually fill out this survey, and I want to get your perspective as seismologist of whether or not the published work in the big data, big simulation was in your mind reproducible. And I will look at the survey when they come out, or the responses when they come out. It's anonymous. I am not the pro of Google Forms, but I hope that we'll be able to do that. Do you all have it? Do you want me to show again? Yes, that's a good point. So on Slack,
Let's do it now or sometime.
right now, let's do it live. Yay. You can see our live response. We should be about 70 plus 50, maybe 100 response I'm expecting. And so I framed it as, what is the proportion of papers you think are reproducible? We have some pessimists, 0 to 20%. You know, I learned Python because we submitted a paper with a student and I didn't know Python. And I got the revisions and the student had left and I had to work on the revisions and I found a bug. And I was like, this is it. I am never letting a paper go without at least some overseeing. And it was a minor bug, but still, like the ability to see what the student was doing and to be able to be accountable for what we were claiming was super important to me. All right, 65. So we are like halfway, right? So there's more pessimism in the way we should be, your own ability to reproduce these papers. Now, I didn't put that in the survey, but may I ask you, do you feel like it's because it's too much data? Do you feel like the software is not available? Resources? What would you think is limiting you from being able to reproduce it?
In some cases, some of the data is, let's say, protected.
Okay.
So people have taken certain grants, so they are the owner of data, so they want to protect the data somehow for research. In some cases, I think in those cases, it could be possible to give some synthetic data, so you never reproduce the techniques. But in some cases, even in that case, it's not provided. So
that's a great idea. Actually, providing synthetic data to reproduce if you cannot deliver the data, it's a great tool. Somebody's taking notes. Sure, I think that's a great idea.
Because I have the same issue. So for instance, we have some local data that somehow protected, let's say, but we made out some synthetic set of data with the same locations, with some noise. So at least the person is able to reproduce the software and do the same things even though as the actual data.
Excellent. Thank you so much. Other ideas? Yeah.
I use ambient noise. I use cross correlation to test ambient noise. And some of my results are generated by very big computers. So I'm not sure the other people will have the same computing power to generate the result. So I'm not sure if that kind of not useful or.
I think it's a great debate because I think by the end of the week, we're going to learn ways that we can reproduce or provide ways to reproduce the work, detached from the resource or even from where the data is. We can learn ways to document all the workflow, to reproduce all the results, provided that the user will have access to the data and resource. But complicated workflows for sure. Yeah, right.
I think that question is kind of oversimple in the sense it can't be reproduced is my question. It can't be reproduced with a reasonable amount of effort. That's really hard. That it might take 2 years to reproduce the result of literature without knowing exactly how they did it. We have all the pieces there that we take. Exactly. That's what we need to try. We probably have that different shortly. We're going to take the issue of integration of the software and data together to make it practical.
Excellent. Thank you so much. Yeah, because sometimes the workflow is in the paper, but it's very hard to recode or something. Carl?
I'll throw out one example on both of those. In the SPECPEN package, there's kind of a class paper where they make these nice kernels. And we had an advanced PhD student that said, don't make that kernel and then let's talk. Make the one that's in the paper and do correspondence with the author or someone who already knows the code, knows everything. It took about 2 weeks to get this classic example as a starting point. And now that's in the code as a reproducible example, but it's what you said. You don't know the tiny decisions being made. There's not enough information. That's, to me, the biggest hurdle. We don't explicitly say, even processing a single seismogram, you don't know the corner filters and so forth. So those decisions, but then the other one, just like, who has 2 weeks in their PhD in their 4th year to go do this service project for the rest of the community? Well, that's what a research assistantship is, but it doesn't always align with the thesis.
Hey, Bru?
Example, your practical landscape.
Yeah. Yeah, and I think what we are slowly moving toward as a community is we're starting to embed this principle from zero, from when we start our projects. We just have to really account for this goal of reproducibility for our own sake, right? Because when we submit some revisions to a paper, we don't want to be lost in finding all the files, right? But also for the community, if we start doing that from scratch, you save a lot of time for future efforts. Ebru, she's always.
Yes, I totally agree that we take to document it. We take to make it, we take to provide our data for the producers. But on the other hand, with the both seismologists, the geophysicists who complain that, we get the pressure to publish. And this just takes lots of time. How are we going to balance this? Or how are we going to get credit for this?
Yeah. So I think if we put that early on in the workflow, we start being organized. I'm a mom. I have to be organized. Otherwise, it's a chaos. It's still a chaos. But it's the idea that if you start building these habits from the beginning, you will gain efficiency. I think some comments were about also in the Zoom about lack of data availability and lack of computing resource. That could be a reason why we cannot do that. And I think it's particularly true in the context of big data and big simulations workflow, right? We have this even more complex mission to demonstrate reproducibility, but it does eat up a lot of resources. So in that survey, there was a paper from Nature a couple of years ago. Excuse me, I keep doing this. This is the personal question. Are you able to reproduce your own work? And this is where it really hits home for me. I'm looking back at my pre-2018 literature, and some of these papers where I use Illustrator to update and make this figure nice. This is not reproducible, right? And so I look back at my, PhD time, and I spent so much time manually tuning my figures. I'm never going to be able to reproduce it. Or even looking at the codes that I use for a paper, the pre-2020s basically are eras where we are not really encouraged to do reproducible work. And that means also I did not build that habit. So anyway, I just wanted for that to hit home, some of these different disciplines have a lot of laboratory experiments. Anything with life science, with bugs and cells and whatnot, it's more complicated than what we do. We have the opportunity to do theoretical work, which is, reproducible by nature, or data that's already available. And so we have the opportunity to do this on our own. So there's a lot of scientific literature now that is supporting the idea of doing reproducible science. Don't feel guilty about the past. Just embrace it today. That's been the kind of the spirit. Take small steps to improve it as time goes. It's not something that is hard. There are small, simple steps that we can all take to start doing reproducible science. Some definitions from John Kerbach and Kerbach in 1992. I love the literature on this topic. The actual scholarship is the full software environment, code, and data that produce the results. So when we talk about reproducible science, we talk about software environment. This is your dependencies and the data that comes with it. And what they commented in this paper in 1992 is reproducible extra work. It is in the short run, once you build a habit in doing so, but in the long run, you gain efficiency. So it's the transition that's hard. And then once you have it in your workflow, then it's much easier. Why is it worth it? It improves work and work habits. It makes people check your codes. I've had advisors checking my codes, and I was like, ooh, it's my code. I must be right. Don't look at it. Well, they looked at it and it was wrong. That's the point, right? It's like we're correcting ourselves. Having others check your code is super important. It improves teamwork. And we as scientists tend to think about our big single author paper, but actually a lot of the cool work that we do is built on this diversity of ideas and expertise. And so biggest scientific papers come out from teams. And if you don't work in academia, you will be working as a team. So there's no way around this in learning how to do it. Greater impact, you have less competition, more collaborative work, which can only gain. It's just friendlier in general. It also helps because the more colleagues you have, the more acknowledgement, the more citations, and they just trickle down and you just get, it's better for your career as well. It's also more effective for training and advising for faculty. That's why we also have a lot of faculty members in this training workshop here. It's because I want to make sure that these are something that they may want to adopt for their own teaching style. And also there's the idea that research is a public good, public funds pay for the research, and everybody should be able to access it. Okay, so in doing so, when anyone can understand and replicate the steps of the analysis, so this is kind of explaining what does it take to do reproducible work, transparency in data collection, processing, analysis. So this is explaining your workflow in your paper, to code, to documentation in your paper, public availability of the data, and associated processing methods, transparency in communication of the results. These are all the steps that can help us work toward reproducible science. So we may want to talk about computational reproducibility. This is where the detailed information about code, software, hardware is in maybe the publication. So that can be in that form. Empirical reproducibility is when detailed information is provided with non-computational empirical scientific evidence. So that can be done when making data and details on how it's collected freely available. Statistical, these are definitions, statistical reproducibility. Detailed information is provided, the choice of a statistical test, the model parameters, the threshold value. This is maybe what Carl was mentioning on these tuning on the filtering processing, like what did you choose for your filter bandwidth in your data processing? When all of these parameters are made available and all these stats, then that's what it accounts for. Now, I really like this table. This is out of the Turing Way Jupyter book, which has been an inspiration for a lot of my own teaching, is when they talk about, they want to discriminate between reproducible, the same analysis steps performed on the same data set, pure reproducibility, that's almost like correctness. Did you do it correctly? Replicable is the same analysis performed on a different data set. This is what we try to do in science for observational seismology. We learn about earthquake processes in California, and then we want to understand if that same thing applies for the earthquake in New York State. Something like that. We can also talk about robustness. The work that is done, the work is not dependent on the specificity of the programming language, and the results are the same. So this is coding Python or Julia, and then you get the same answer, or C and Python, and we get the same answer, or not. And the grail of our scientific investigation is generalizable. Different data set, different code, same scientific outcome. And this is where we can really gain in advanced science, is once we demonstrate this. And you can tell this is a lot of tedious work that is not something we always do as a science, but maybe as a community we can organize ourselves and try to allocate, who would work on what pieces of this problem. So I really like to cast it this way. Some notes on reproducible science in the journals. So Biostats was one of the first one that was asking authors to have statement on reproducibility. They had statement on code availability. Authors are strongly encouraged to submit code supporting their publication, and they have ways to show that. I gave that lecture a year ago. I feel like today this is just going to happen. Every journal is going to ask for this. So it's no longer going to be a transition. It's just going to be not even a choice. Excuse me. Didn't anticipate for this thing. So it is mandated by some today, and so you're just going to have to do it. Some definitions also about open science in general. We have open access literature, open data software, accessible to scientific process and knowledge. All of this is, I think this wheel was from the AGU definition. I found other interesting literature on open science. This is from Vicente Saez 2018. Open Science Now, the title was a systematic literature review on a integrated definition. And so what they stated there was it's a transparent and accessible knowledge that is shared and developed through collaborative networks. And they define knowledge as an umbrella term used for code, data, scientific output, results, publication, and whatnot. They also express the difference between knowledge and what it should be: transparent, accessible, shared, and collaborative developed. So a few other things. There's just so much literature now on this, but open data, software, hardware. This is the hard part with our big simulation or cloud computing is the hardware are these massive computers that only a few tend to have access to, given our expertise. Open notebooks, we'll be doing a lot of these. Citizen science, DEI, and open educational resources, which is also the root of the workshop we're running here. Meant to be open to everyone. Anyway, lots of definitions. You can keep checking through that. Just a note on what we want to talk about here is open data and open software more precisely. The fact about the idea of doing reproducible work also means that in terms of open data, we want to be systematic in how we analyze the data. And so we tend to say, don't play with the raw data. The raw data stays as is, which is nice for us as observational seismologists, where the data is hosted on the IRIS or the EarthScope data services. This is our starting point. We start from that data. And what we do is everything about the processing, the downloading, the processing, all the pre-processing, removing the instrumental response is something that we should be able to reproduce. And I remember this 5-10 years ago, I would download, remove the response and store on the file. So then I would start from there. But I would start from the data that had the instrumental response removed. That includes a processing on it that I did not necessarily document in my papers. And so what we want to do is the data stays untouched, we document, we code well, everything from the basic filtering, the merging, all of that can be saved. Okay, and it's the advantage of that is you're not also doubling storage. You don't have to store your data locally. You just make sure you can pull from what's already, somebody's paying the bill for storing the data, and we just look at the processing, we just keep track of that. It's basically a small YML file and a piece of code to redo everything. We have to make data easy to understand. In machine learning, seismology, this is very important. We tend to curate a lot of seismic data and their metadata, so we have to really document everything clearly, make it easy to use, and try to cite with DOIs. When you create data products, you probably all know these by now, but Zenodo is a good platform to store your data products, CSV file, maybe an earthquake catalog or whatnot. But these other platforms that other infrastructure to host data as well, they all have their own pros and cons, but they all give DOIs, persistent identifiers. Maybe some of you have seen the Wilkinson paper 2016 that talk about the FAIR data. So I think that's old school now, but you have some of these ideas of what is fair, findable, accessible, interoperable, and reusable. These are the principles for what FAIR data is. And most of the repositories today are considered as fair because of their persistence identifier and their openness. So that's some of the data. For EDU journals, when you submit your data, the data, if it's not from a public archive, has to be deposited in a repository shown before. So this is going to be a requirement for most of the EDU journals. And the data availability statement has to be clear. So Felix, in your example where you said the data is not accessible, but I created synthetic data. This is an example where your synthetic data, I guess, was hosted on Zenodo, was accessible, or maybe there was a way that you could recreate that synthetic data. And this is where it can be studied here. I find challenging when we do big, massive data analysis to have the DOIs for every single seismic network. And I don't think there's a good option, but Shibin, for one of your papers, did not you have like 1,000 DOIs or some crazy numbers of like each network was listed, and we did not know how to cite all of the GSN networks and all of the temporary networks. And I think that's an active discussion actually in the Scope data services, is how to properly cite all of the networks when you have these nice open archive. So I think that's quite interesting to be solved in the future. But they each have their own. So
and then see which network you are using and then exactly what it is. That's the first site.
The network, yeah.
It's
Mm-hmm. Yeah, it's interesting. You know, we produce DAS data in this university, and so we go through the university to get a DOI and make it publicly accessible, because there's no DOI yet for these temporary networks. So it's definitely a challenge. I don't know why I talked about Nature. I don't really like that journal, but at Nature, the very open journal, authors are required to make materials, data, code, and associated protocol available. So this is part of the submission process for Nature. And then you pay $15,000 to get published. AAAS journals for the science also require that all underlying results have to be publicly immediately available after their deadline. And they also ask the submission that the authors to make sure that the data is available, and no statement should say contact the author for accessing the data. They also talk about making making all the formats community standard and machine readable formats. So no obscure binary format for your file. Everything has to be readable from either ASCII or like a text format, or a well-documented metadata to read your binary format. So there are a bunch of data journals. So there is EGU, Earth System Science Data, Geoscience Data Journal, Scientific Data in Nature, SR Data Mine, and I think Seismica, Tectonica, and Volcanica also have ways to publish data. A note on open notebooks. This is the idea that your entire workflow can be documented in a notebook that mixes text and code. And so we'll be using a lot of these in this workshop to document our workflows. So this is really a browser-based way to integrate code, text, and narrative. And so I do like this little cartoon. We'll spend some time on it to show you the process of producing a complex workflow, documented it, and maybe sharing it. So I'll read out loud. Jane, with my French accent, Jane has written a paper based on her experiments. This is for mostly students. She thinks a lot. She would like anyone to be able to reproduce, check, and improve her calculation. She describes the experiment as is in a notebook that mixes prose, some equations, code, and visualization. She publishes them on a publicly hosted repository, GitHub, Bitbucket, or GitLab. She makes that repository binder ready, describing the software required to run the notebook. This is the open hardware. It's the idea that you can create a container that would then spin on an instance, a node, and upload all the docs and run the software. And as a result, step 4, everyone can now run and reproduce your entire calculation. And I think this is something we can work toward. We'll have a lecture today on containerization. This is the way we can work as scientists, by looking at describing with text, code, visualization, making sure it's all runnable with nice dependencies, accessible on GitHub, and making it containerized so then people can just open the container and run the workflow. For big data, big simulation, that entails just being able to reprocess of the data that can be caught from elsewhere, or have all the parameters for the simulation stored in a small file that you can then run. Okay, sorry, this is a long lecture on open science. Just a thought on like, what does that mean fair for software in the Gill-Wilkinson 2016 geoscience paper for the future. They also described software, so it's not just about data. And so they describe guidelines for making software fair. They talk about accessibility, documentation, the small approaches, and the advanced approaches. And in 2022, there was also a paper that came out specifically about scientific software or research software. And what they described, this was a result in Europe as of a collaboration and community efforts to define what the guideline will be for research software. And I'm just going to summarize it here because this is relevant to our community. Software and associate metadata to the software, it's human and machine findable. The software metadata and its metadata is retrievable, accessible via standardized protocol like Git would be one example. Software is interoperates with other software. This is super important by exchanging data or metadata through APIs. This is us using UpSpy as an interoperable ecosystem for managing data. That's one example, but there may be more. Software is both usable and reusable. And this is the hardest piece, I think, for us, is we can write our own software, but we are not in somebody else's brain. So when we share software, we have to document and to make sure that others would be able to reuse the software. Otherwise, this is never going to be a useful product for the community. But it's the hardest piece. The geoscience paper also talked about workflows. And this is complicated when we have download the data, pre-process it, merge it with something else, mesh some kind of velocity model with this. You can see how the pipeline becomes complicated, but we just have to be organized and keep track of all of these steps and either write it in text in a paper or have a more sophisticated way to describe it. Okay. I'm kind of tired of talking, so I wanted to go show you, the idea of open access being quite an important challenge that we're facing, but our community, especially, I don't know if Alice is still online, but Seismica was one journal that tried to really tackle this problem of open access for papers. It's, sorry, the preprint is, sorry, this is it. It's the idea that a lot of papers are still not accessible to the public or to us, to ourselves, and yet some publishers are still making a lot of money out of it. And so to get around this, the community has defined new standards for open access, and Seismica is taking on the challenge. Another thing I want to point out is the idea of really the growth in preprint servers and making your papers available on preprints as soon as you submit it and you get a DOI for that paper. And it's very tempting for our community because the paper may last maybe a month, 2 months, 3 months, 6 months in the review process, and we're ready to, demonstrate our work and publicize it. So we have this tendency to put out our papers in these preprint archives. The one thing, though, is I really value the peer reviewing process, even though it may be unfair, random, comments can be completely wacky. I do think that peer-reviewed papers should still be seen as unpeer-reviewed and unchecked, right? The point of peer reviewing is that others, even though they're not selected the way we wanted them to be, others are able to check your work. And so it's very important that when you look at the literature, peer reviewing is the kind of only gate that we have for checking correctness and all that. So I recommend that in general, be careful when reading non-peer-reviewed work, and also say be wary of peer-reviewed work because there's still papers that are unreproducible and unchecked. Okay, so I kind of want to, at this point, I'd like to, there was I don't know if Alice is online, but last year we gave this lecture on Seismica, and I can show just a little bit about it. Seismica was a journal that was really community-led, community decided, and community maintained today. And so it's a journal that publishes quite fast, it's free, it's typesetted by some of your peers. It's just really groundroots efforts for open access and transparent process. So recommend submitting there and maybe contributing even to that journal by offering your service. Okay, so I think we're kind of done for this idea of this first lecture on reproducibility. And I'd like to open it up to questions or comments or vibes that you feel, or yeah, Gary.
Fundamental thing, even especially first line distinction between interpretation and a fun thing because the kind of intellectual side and the interpretation side of information and ideas and how we apply it. Over time, this idea of reproducibility is not about that. It's about how you got figures for the interpretation. You cannot reproduce that figure. Then you have a problem. And that's the problem with our work. There's too many things that are too hard to do. But I think everyone needs to understand that difference in context of what reproducibility means. It's not about the interpretation. Some people would call it science and result. That's not really true. Intellectual output of what that data was. That's not what you have to reproduce. That's in your head. How you understand the word. But it is important about how you make it fit.
Yeah, thank you. That's good. I'm taking notes. More mature, more ideas. Any other thoughts? Have you tried to reproduce your year or 2 years old work before? Yeah, I see like, oh my God, faces. What are your tools to kind of check yourself on reproducible work? What do you impose on yourself if you do any? Renata?
Yeah, because one of the older some of these technologies that go away, right? So there's still a really important place for just describing in words all the processes that we do. Because like some of the technologies that I used back in the day, old portrait clothes, etc. You can all find those, right? But just keep in mind that some of these tools might go away, so it's still really important to describe in words all the steps you have to do.
All right. Any other thoughts? Coffee? Coffee. Okay. I'll pause there. Well, thank you so much.
Good. Okay, we can start. Thanks for joining, everyone. So before we really start the session, I hope you're ready to have the proper install. I think we actually sent out instructions. I'm not sure. We sent out too many instructions, I guess. So I'm not sure which version you get, but we have different options to install on the latest ARM-based Mac OS. There's a older Intel-based. And for the Windows users, when you install Docker, make sure you're using the WSL, Windows subsystem for Linux. That's the option. And don't do the Windows container thing, because that will not work with most of the containers that we will be using for the week. Oh, Yeah, I need to stand here, I think. Oh, and this connection is not very reliable. Oh, yeah. Okay. Where's my camera? Here. Okay. Can everyone hear me? I mean the remote folks, of course. Assume so. Okay. Well, anyway, for the Windows users, make sure you're using the WSL option rather than the Windows container option. Those are mostly the caveats. Other than that, we can start. So this is really intro to containers. Basically, I'm going to walk through what containers is, how are we going to use them, the basic and boring stuff, which you can mostly find in Docker's documentation, but we'll just have to go through it anyway. And in the end, I hope we have some time to actually run and use the scoped base container to containerize your application. And that could also be a homework too, actually. So anyway, let's get started. Enough of it's not forwarding. Okay, container. Hope you all know what container is. Of course, there are boxes, right? But inside the computer, of course, a container is not a real box. It's really a box for you to put things in it. So it's isolated from the outside. By saying outside, I'm saying isolated to the host. That's your main operating system. That's what's been running on your laptop. So it's well, that's the definition. I'm not going to really read it, but basically the idea is once you have the isolated, what's inside the container, it will actually have a clean, uninterrupted environment that can be used for the specific application you're going to be using. And however you run, whatever you run inside the container, it will not interfere with the outside, okay? That's the whole purpose. So the whole idea is to actually ensure portability of your software and reproducibility of the code that you are running or workflow you are running, right? Basically, well, Maureen just talked about reproducibility, and we know it's actually difficult because, it's not just about data and your code, your application. It's actually more than that. It's where you're running it, how you're running it. It's actually the running environment that also controls whether the thing that you run, the data you process can be reproducible or not. And that's where comes the container, which can help you to ensure reproducibility by giving you more control on the environment of the code that you will be running or the data you will be processing, okay? And the other nice thing about container is that, well, I can move on to the next slide, I guess. Is that, it sounded like a virtual machine if you ever used it. I mean, these days, virtual machines are pretty rare because of container, but, for some of the older folks, I think you probably use virtual machine and think virtual machine can achieve exactly the same thing, and that's true. But what's nice about container is that it's a lighter weight virtual machine, meaning that for the virtual machine to work, sorry. Yeah, that's too bad. It just keeps disconnecting itself. Sorry about that. Yeah, maybe. That's not okay, that works. I'm not gonna touch. Oh, I still need to touch it, of course, unfortunately. This thing. I didn't even touch it. I already changed a different USB, but it's maybe the cable being too heavy. Yeah, do you have an adapter? Sure, I can try yours. Yeah. Let's try this. Thanks so much, guys. Did it work? Not even showing up. Oh, that works. Okay. The slideshow again. Need to share screen. Oh. Okay, maybe it's I'm stepping on the cable. I don't know. No earthquake. Okay. Did it work? But it's not. Oh, okay. Now it works. Good. Sorry, now we're back. So yeah, it's a lightweight virtual machine, of course. It doesn't need to run all the other heavy stuff that usually a virtual machine involves. That's what's nice about container, and that's all you need to know about from a user standpoint, okay? And now we talk about containers. Naturally, the next topic is actually a Docker. So I already asked all of you to install Docker. So Docker is really the most common container runtime or containerization platform nowadays, because it's actually a company. It's an open source project, well, starting from the beginning, but now it's kind of a company behind it to provide the service. That's kind of the open source model these days anyway. And Docker helps you to create, deploy, or run the containers on your machine. And that's why we asked you to install Docker. Of course, there are actually some Docker alternatives. In particular, we are actually talking about the Apptainer, which is widely used on HPC later on in this session. Okay. So this is the whole Docker workflow. So there are actually a few concepts in this plot, right? So basically, there's a Docker file, which is the file that defines what an image is, right? With the Docker file, you can then build a Docker image. And that image, is really the whole thing, the containerized environment of your application, of your data, of everything that can be run as it by itself. Then if you do a Docker run with the image, you created a Docker container, which is actually a running instance of that image. It's actually a running instance of your code, inside the image, of course, right? And also, you can push your Docker image to a container registry, like the Docker registry. There are also a GitHub container registry too. But basically, the registry is a platform that hosts the container image. It's like a GitHub that hosts the source code, right? For people to gain access to those images, okay? So we are actually gonna talk about each one of those components, the Docker file, the Docker image, the Docker container, and the registry. First is the Docker file. So Docker file is really just like a make file, if you're familiar with those. It's really just a bunch of lines that defines, what makes the image, right? So there's usually a from line that tells you are building the image from another base image. And this is actually an important concept. You always build your container from another existing container. So for example, like in this case, we are actually building from the Ubuntu 1804 container, right? Meaning that once you enter the building process, you already have Ubuntu available. Then you actually basically run commands. So you use the run clause to define the apt get update, apt get upgrade, whatever. Your standard practice on building the code, building the environment to run your code, and all that. And then there's the env, basically that actually defines the environment variables inside the image, right? So you will have, how do I get rid of that? Okay, sorry. So for example, here we actually define the path, which contains the code we just built, the pi, whatever. Okay. Yeah, well, I'm actually not going to go into these details. We will be sharing the slide. This slide really serves as a user manual or documentation thing if you're interested in looking at it, but going through every single details will take too much time. And I don't think that's of the best interest of all the participants anyway, right? So from run tells you what run does, tells you, yeah, so well, there's one caveat. So each run instruction actually creates an intermediate image. Okay, so if you look at the Docker container image, it's actually built with multiple layers. As I told you, we always build from the base container. The from line defines the base layer, right? So you're actually having a layer from the from line too. Then your next run line basically builds on top of that. So it's another layer. So once you end up with building your image with the Docker file, you end up with a lot of layers that actually compose of the image itself. Okay, so, but that's really the details. You don't really need to know. You just need to be aware of that, I guess, from the user standpoint. There's a copy line that actually copies the code from your host directory into the containers directory. We don't need to go through the example, but basically this is building the Pi code. Simple, not very useful. Okay, that's the Docker file, then that's the Docker image. So once we went through the Docker file, we will actually build an image already. So that Docker file itself defines the image, okay? Yeah, I talk about the layers, not important. Okay, so once we have the image, now we can actually have the container. So container is again, I said that, right? It's a running instance of the image. It's an instance of the image, meaning that you can spin up a container, you can make changes inside the container, right? You can, once you have the container running, you can add more code to it. You can, install more package to it. But those things will actually happen inside the container that will not affect the original image that you actually run it from, right? Oh, of course, because of that, if you did anything to your container, the running instance, and you actually stopped it or removed it, then all the progress, all the work you've done inside the container will be lost. That's important to keep in mind, right? So to make that not being lost, you actually need to save the files inside the container to the outside. Then you can safely delete your container instance, okay? And with the containers, then there's the image registry, okay? So again, I said that, right? It's basically a platform that stores the Docker images. So the most popular one is actually Docker Hub that you might heard of already. That's basically hosted by Docker. And there's also an open source one that's, well, not necessarily open source, but it's a GitHub hosted one called the GHCR, GitHub Container Registry. Basically, these are the platforms to publish your Docker images for public access. And that's actually one important chain of the reproducibility, right? Once you publish your container, anyone else can supposedly, download your container image or pull your container image and then spin up a container, a Docker container instance locally and run exactly the same code from within exactly the same environment that you define. Okay. Of course, these image registries always have tags to identify different versions of the same image, right? Just like in GitHub, you can actually define tags to your source code. It's the same concept. So with that being said, a usual container image name is of such a format. Okay, so this is the name defined of a container image or Docker image. So basically, it starts with the registry's name. So here, if we have a container on the GHCR registry, it will start with ghcr.io / that's the owner name. So for the site scope organization, site scope is the owner. then, well, here I'm actually using the adjunct tomo container image as an example. So the actual container image we are running is called adjunct tomo. So that's the container name after another slash. Then there's a column, which you can actually put a tag on it. So for example, here, I just put a nightly tag, meaning that we want to pull this image that's being built nightly inside the repository. So they always have the nightly tag, of course, right? You can define your own tags there. So when you do a Docker pull to pull images, this is the naming convention you need to follow. Well, of course, there's one exception, which is if you're just pulling some image from Docker Hub, you don't actually need the first part, the registry part, because by default, if you're using Docker, Docker will just pull from Docker Hub. Then you don't need to define the registry again, right? Of course, if you're using other runtime, then you do need to define, even if you are using a Docker Hub. Okay. So we actually went through all these components fairly quick, okay? Now we can actually get to the real work. So, so here I actually want to make this a little bit interactional. Basically, if you have your own code that you want to containerize, you can actually start following the steps. But maybe I should just give you some time working on that later on. So I just quickly go through each steps needed to build a container image by yourself, okay? So basically the most important command is the Docker build, okay? So you need to write a Docker file, save it in your local directory, okay? And the name is Docker file, obviously. Then you can just run the Docker build command and use the -t to give it the, actually, well, T means the tag, but actually you can use -t to give the image you are building a name. And if you want to push it to a container registry later on, you actually want to have a name that actually follows the naming convention I just showed you, okay? That's the Docker build command. So once you do the Docker build and finished, you can use the Docker images command to inspect the local images, the images available locally on your laptop, right? So if you do Docker image, it's actually show you, okay, there's a username / PyEstimator image that we just built from the previous command, okay? There's also a Ubuntu image. Why is that there? Because that's the base image we are building from. So it's really, by building the PyEstimator, we are also pulling the Ubuntu image from Docker Hub already. So the Ubuntu is now local on your laptop, right? And that's what's the nice thing about these different layers. So this Ubuntu image can be reused by other projects, other images that you will be building in the future. You know, it's not going to save another copy of it. It's just going to be there as a layer. And then that layer can be used for any other container you'll be building locally again. So once we have that image, we can use the Docker run command to, you know, turn that Docker image into a running instance, Docker container. So that's the Docker run command. This -it means we are actually using an interactive terminal to run this. So basically, with that -it specified, we can use /bin/bash, meaning that we are actually execute the bash command inside the container instance. Okay, and because bash is interactive, so we need to tell Docker when you run it in the interactive mode, then we actually get spawned into the shell, the bash shell of the Docker image, the Docker container we are running. One important argument is this --rm, meaning remove. So this argument will tell Docker to remove this container instance after you exit from it. And this is important because I told you, right? Whenever you do a Docker run command, it will actually create a new container instance. And that new container instance will actually take up some storage space on your disk, on your hard drive, right? So if you don't use --rm, even if you exit the container, the container itself will still be saved and stored in your local storage, taking up the space. So if you're just running something, like out of scratch or something, you don't want to keep the result or anything. You always use dash rm so that this new container instance being created will not actually consume your local storage. And because Docker images are large, each container instance is also large. So if you just run a lot of Docker run command without the rm, without removing them, for the laptops that actually have small amount of storage, it will actually run out of storage really quick. That's usually the caveat. Okay, so once we are actually inside the bash shell, you can actually see your command prompt will change. So now that's actually indicating we are actually inside the container. And once we are inside the container, we actually have the environment that's defined in the image, such that I can run, this. If I do ls code, you can see the py there. Then we can run that, and it actually does this work, right? And it's actually inside the container. There's none of that py estimator thing outside of the container on your host system. Okay. Of course, this is really just showing you how to run it non-interactively. So basically, you don't need this -it. You can directly issue commands to it. So you can say Docker run your container name, the py, give a number, and it's gonna do the py estimation for you. Okay. Okay. Also, it's always important to share your Docker file once you define it. So in practice, what we usually do, we just put the Docker file inside your Git repository, actually, right? So basically, you can just follow the standard Git commands to save your Docker file. And there are actually two different ways, right? So you can have your Docker file or Docker container build steps defined as a standalone repository, but you can always, put that in your existing repository, just like a makefile thing, right? In your source code, you usually have like a makefile. Well, if you're a C programmer, to actually compile your code. And Docker files serve as the same purpose. So the Docker file is like, we can use the Docker build command instead of the make command to instantiate Docker runtime to build a container for you, right? Anyway, this is designed as an interactive session, but I figure it's not necessary to do it that way. But you can add tag to it whatsoever, not important. Okay, now we have the Docker image being built locally. We want to share it to the public. What we need to do is we actually, being able to share it, we need to have an account on those registry platforms, right? So the easiest is to use the Docker Hub because Docker is built around Docker Hub ecosystem. So if you just use Docker login command, it's actually asks you for username and credentials to log into your Docker Hub account. And once you log in there, you can do Docker push with your username, right? The py estimator and the tag you just created to your own container registry. Okay, anyone can do that. That Docker Hub account is actually for free. You can always create it anytime. And the storage space is also for free, meaning you can even push large containers to Docker Hub. Well, I think there's a size limit, but I'm not sure what that is because I've never hit it. Okay, I've pushed like several gigabytes of containers to Docker Hub before. I never run into issues. Okay. So once you push to Docker Hub, then on a different laptop or someone else can just use the Docker pull command to pull the container you just pushed, with the same naming convention, right? So we're doing user name / py estimator column 0.1. Okay. So just a recap of all the core Docker commands that we kind of we will be using. Okay. So we actually went through the Docker login, Docker images. There's a Docker PS, basically lists the running containers. Okay, those are the already running container instances. Well, it's like a Docker image. Docker image shows you the images. The Docker PS shows you the running container instances, right? There's a Docker pull, Docker run, Docker inspect. That's not important actually, but basically it tells you some metadata information about the image. There's a RMI, which is used to remove a specific image. There's a RM, which is to remove a container. Remember the difference between the image and container, okay? That's always confusing, but image is the static thing and container is the running instance, okay? There's a Docker stop. If you find any Docker that's running with Docker PS command, you can use Docker stop to stop them. We have the Docker build, we have the Docker tag to actually add a tag to an existing image if you need to. And we went through the Docker push, okay? So these are the Docker commands. Yeah, next topic is app container. I told you, because we are going to be running some containers on HPC system. So this is the next container runtime I want you to be aware of and being able to use. And that will be helpful for the rest of the week for those sessions that's running container on HPC system, okay? So app container is really just an alternative to Docker. The reason people use app container on HPC system is that, for Docker runtime, you've all installed it right now, I guess, is that it actually requires the root privileges of the system to be able to install it. And it actually also requires the root to be able to run it. So now there's actually rootless Docker, but still, if you're just doing everything by default and not really understand Docker very well, it still requires root. And that's the reason it doesn't work on HPC system, because on HPC, it's a shared cluster, so people don't have root access. You will need to use the alternative. And app container is actually designed as a container runtime that can run Docker containers, but without root access, okay? So it is actually the most popular container runtime in the HPC world, okay? So there are actually some key differences. One important one is the host directory. So in Docker, the environment is always isolated. Inside the container, you won't be able to access anything outside of it on your host. But with app container, it can actually, well, you can also mount or byte mount your host directory into the container. But app container, usually there's by default, it mounts your home directory or work directory. At least that's what's being done on the HPC cluster from Terra that you will be using for the rest of the week, okay? The user ID is different. So with Docker, because you have the root privileges, you can actually be as the root inside the container. But for app container, you cannot, right? With app container, you can run the container as root. Then inside the container, you can also not be as the root, because if you're root inside the container, you'll be able to modify, make change to the files that's being mounted inside the container, which violates the idea, right? So inside the app container runtime, you are still as the same user as if you are actually outside the container. So basically, you can think of it this way. So app container is a less isolated environment than Docker, okay? You actually share the user namespace inside the app container, and then your host. But with Docker, you're completely isolated. The image format is also different. So app container defines its own image format. That's nothing new, I think. Different software implementation will just have their own format. So Docker just have layers. I just show you. But yeah, I don't think there's anything that different than the fact that with app container we just need to have a specific image file. Rather than Docker, there are actually layers being managed by Docker runtime itself. We don't necessarily can look at or inspect those layers, right? Yeah. So this is actually the development workflow if you are actually running on HPC. So because sudo is not allowed, sometimes when you're building your container in your Docker file, you actually need sudo. And in that case, those containers will not be able to be built with apptainer. So we usually build a container on a different system, on your laptop where you do have root access. And then you push the container image to a public accessible repository or registry, actually. Then on HPC system, we use apptainer to pull the container image to the HPC system and then run it, okay? So we use Docker to make the container. We use apptainer to run those container, well, to make the container image. We use apptainer to run those container image on HPC system, okay? So, well, now I'm actually going to go through some commands, but you can see it's actually pretty similar to Docker. So apptainer, there's also apptainer pull. And yeah, the format is a little bit different. So if we want to pull from the Docker hub, we actually need to say Docker column //. And then the rest of the naming convention is the same, okay? It's really the registry parts being different. Yeah, well, so if you need to spawn an interactive shell, you use apptainer shell command. If you want to run something directly, you just do apptainer run, just like Docker run. Okay, if you want to execute a specific command, you just do apptainer execute, give the container name, and then the command to be executed inside the container. So apptainer exec and apptainer run, combining the two is like the Docker run, okay? But I think people just use them interchangeably, and I think nowadays apptainer exec and apptainer run are pretty much the same in terms of functionality. Yeah, and on HPC system, which I'm actually going to talk more about that this afternoon, you will need to actually submit job to run your container, right? So you define your job script, you do module load the tag apptainer, and then you use the apptainer exec or apptainer run command to run your container. That's the usual workflow, okay? Well, yeah, now I'm going through the pull command, the build command. So you can still use apptainer to build container images if the building process doesn't require root. And that's the command you can use. So apptainer build, and that will actually, so SIF is actually the container image file format defined by apptainer. So you actually see a lot of those there. So you can just do apptainer build, container base, whatever. And we are actually building it. So this command actually builds the container image file from the Docker hub container registry. And that's the name of your image you're actually pulling from, okay? Of course, apptainer has its own Docker file, but it's not being called Docker file, it's called the definition file with the def. There, so you can always build a apptainer container with the def file, but that's not important. We are not doing any of that, okay? Yeah, just really recapping all this command we just talked about, right? So there's the apptainer shell that spawn the shell inside the container. There's the apptainer exit. There's the apptainer run. This is how you use the apptainer at tag. Okay. This afternoon, once we have access to HPC, we'll actually try those commands. Okay. Right now, don't worry about it. Not that important. But apptainer also has cache. Okay, so you can do apptainer cache list and cache clean to delete unnecessary images or that you created, right, from your previous pull commands. One tricky thing is to make MPI and GPU enabled inside the container. I hope some of you understand what MPI is. For HPC code, we always rely on MPI to run distributed computing on HPC system, right? So we use multiple nodes, and these nodes need to be coordinated. They need to talk to each other. So that's what MPI is being used. So actually, app container supports using MPI inside the container. Okay. So basically, what we need to do is inside the container, it will need to have the compatible driver and the compatible MPI version as of on the host. Meaning, if we are running on Frontera, we'll need to have the same version of MPI inside the container, and your code need to build on top of that MPI version to make it run with MPI distributedly on HPC system. Okay. So at TAC, we actually defined a bunch of base images for you to use. One thing I want to point out is we are actually doing something similar in Scoped. So we actually define a size scope container, a container base. So that's actually the base container we are actually building for the seismology community. It actually has the MPI library built in that's actually compatible on at least TAC's HPC systems right now, but we can support others too if there's a demand. But basically, if you are using our size scope based container, you can run the container you built on any of the TAC HPC resources, okay? Including locally, of course. Yeah, let's skip that. Basically, it just shows you how to build an MPI-enabled container with the size scope based container. Okay, just do Docker build, Docker push. We kind of already did that, right? And then you can actually test it. It runs locally with Docker. So with the scope based container, you can use MPI run inside the container to run your MPI code locally. But on HPC system, you can actually use well, here we use IB run, but it's wrapper around MPI run. So the MPI run will need to be outside of the container runtime so that MPI instantiate those containers and each containers will be able to talk to each other within the MPI environment, okay? We are gonna actually try that this afternoon if we have time, okay? There's also the GPU containers, but right now, size scope containers doesn't really have that yet. But we can make that too, because GPU situation is a little bit more complicated. Well, I mean, using it is actually simple. All you need to do is specify the --nv flag to your app container command, which will actually enable the GPU hardware from the host inside your container, okay? But then inside the container, you actually need to have a compatible version of CUDA to make your code being able to use the GPU from the outside. So TAC also has this base container, the GPU-enabled base container built. We haven't really integrated that into our scope-based container yet, because, well, I mean, the demand is not that very high at this point, but we will be working towards that, okay? But these are the commands. But basically, you can see all you need is this --nv flag to make the GPU-enabled container to run properly, okay? So the last session, I want to talk about the scoped container support, okay? Basically, well, this is what scope is. I think, well, maybe Marine didn't show this specific architectural framework, but basically the idea is we are actually working towards building a science gateway, a seismology gateway, okay, for people to run things seamlessly through your website. And then through your website, you can run your code, run our predefined code or containers on HPC system or on cloud resources, okay? That's what Scope Gateway is. And the core of it is that we actually need to build a bunch of containerized applications that can be run behind it, okay? So this is actually the ecosystem of the scoped containers. Basically, I showed you already, right? We defined the scope-based container, and we actually have different flavor of it. So we have containers that's mostly built for the cloud environment, and we have containers that's built for HPC. For example, in HPC, MPI will be important. That is actually integrated already. And for cloud, we figure people tend to use, Jupyter Lab environment. So for those cloud containers, we actually have the Jupyter Lab built in. So you don't have to install Jupyter Lab you just need to enable your code, then the scope-based container is already having the Jupyter Lab available. Then, from these two flavors of containers, we derive the actual application containers, which some of them will be used throughout the week in the later sessions. For example, MTUQ, adjunct mode. I'm not sure if we're running the SpecFan container yet, but CISO is definitely also one of the containers we'll be using. So these are really all the containers that's already enabled by Scoped. And we actually want to shout out to the community and contribute more of your code. And you think it's valuable, and we want to include that into the Scoped container registry using the Scoped base container to containerize them, okay? This is really a community effort. Yeah, I already talked about that. Blah, blah, blah. We can skip that, okay? So this is how you can run the scoped containers, okay? How you run it locally with Docker, how you run it on HPC system with AppTainer, and how you run it on the cloud. Here is an AWS example inside the EC2 instance, whatever. Okay, you can read that later, doesn't matter. So yeah, so this is really the most important part. So to actually make it easy for you to build your application using our scope-based container, we created this GitHub repository template. This template repository, I guess, that's what it's being called, okay? That's the link. It's under the scope organization on the GitHub. And if you search for the container template, you will find it. Basically, it's a container repository that has all the components needed. So if you create a new GitHub repository from that, it's actually set up to automatically build the containers with the Docker files defined in the repository, okay? All you need to do is really just follow those instructions to change the name of your repository so that the automatically build workflow. We're using GitHub Actions. So basically, I'm not sure if you are familiar with GitHub Actions, but basically with every single push to the GitHub Actions will actually execute a certain workflow that's predefined. So our template actually defines such workflow to build a container using a Docker file and push it to either the size scope container registry or some other registry if you want to define and change it, within the template, okay? So the idea is, to make the community aware of this effort, right? So if your code is built with the base container, the scope-based container, we actually maintain the list of the community contributed applications such that you can actually use this badge in your repository, this badge like scoped containerized, to indicating that your code is containerized by scoped, okay? So this is really, again, the effort of Scope to facilitate the community access, okay? So we want to have a scoped container. So right now, we are not really there yet. So these really are work in progress. So we want to have a scope toolkit built in to these base containers, but we really don't. Right now, it's really just the base Jupyter Lab environment. But we want to have some, valuable software. Well, I mean, OffPy is actually in it. Of course, we figure OffPy is probably the most popular software that's a dependency of any, at least Python code, right? Yeah, so, but we do want to have like a big data analysis tools or simulation applications released with these base containers, okay? And also, once we achieve that, we want to be able to use those containers on the scope gateway. So you can already access the link. I think the MTUQ and MISPass, which are the two codes that you actually will be testing out for the rest of the week. Okay, it's already there on the scope gateway. Basically, you can just go to that website, sign up for an account, and then run the code through the website, but behind it, it's actually executing the containerized MTU, for example, on the HPC system like Frontera for you. So this is really our way to make sure, for the average community users that's not really into coding at all, can still use it, right? They just need a browser, basically. Browser is everything you need to use the scope gateway. Then, things are running containerized on HPC system, okay? Yeah, with that being said, that's pretty much it. We hope to have a AWS backend too, but right now it's not there yet. So now I hope, we have 10 minutes left, but I want to use that 10 minutes for you to try, with these commands to, not with this command, with the scoped template, okay, to actually create your own container image based off the container template repository, okay? And also I can take any questions. Yes, I should.
Let's start. You have a idea for something else?
So yeah, so we'll post the slide on the scoped the event website actually. I guess after the session. I mean, it's I don't. Oh, questions? So first you can use your tech account, but then you won't be able to run anything because you don't have an allocation. Second thing is we actually support the CI logon thing, so you can actually use your institutional account. But then, be aware the scope gateway is still a work in progress. Like even internally, we haven't fully tested it. It's there, but it doesn't really work. Well, at least it's not like that easy as it sounds, I guess. That's the right way to put it, okay? But we are actually moving towards that. Yes. What? Short answer is no, we don't really need it in most of the cases. But the thing is, because people from the Docker environment, they will actually already assume they have the root privileges already. So sometimes, even inside the Docker file, people will actually do like a sudo apt get or something, right? And if you do that, you definitely need the root privileges, right? But if you don't do that, with apptainer, you feel, super cautious and don't use even apt commands. Apt commands actually changes the root directory, which definitely will require the root privileges. But if you just work inside the user space, then you don't need that. Okay. But then all of that is really for Docker. But if you have Docker installed locally, you don't need to worry about any of that. You can just assume you have root privileges. And that's okay, because once you build the image, and for others that actually runs the image, it doesn't matter whether they have the root privileges or not, right? They can still use apptainer to run the container image you build on HPC system without root access, and that's fine. Okay.
You have one question in the chat.
Oh, do I?
The apptainer needed available of the
Where's my window? Yeah, I should. Let me stop sharing. Okay, the question is, does apptainer utilize the native hardware available of the HPC? Like if an HPC is, say, and compute nodes, then can a single container via apptainer fully utilize all the N nodes for parallel processing? Yes, that's the whole idea, right? The idea of using container is because it's lightweight enough that it doesn't really consume extra resources at all. It's pretty much you will get near native performance when running inside the container. And if you are using the MPI enabled container, it's still true. Running it distributedly, you can actually directly access the InfiniBand, the low latency, high bandwidth network infrastructure, such that inside the container or running directly on the host will actually give you the same performance. Okay. And there's a second question: are you using REST API for? Yes.
Can I ask that?
Oh yeah, sure, definitely.
I've gotten involved in providing versions. It happens to anybody who don't manage your environment in these schools. And that's one of the most, Python environment, the container is fabulous because you seal the environment and you know it's the and so that's why we do it. I'm previously with this version that run is like forever. I know it's always the and that's really important point about this. Make a point that it is real.
Yes, and we're actually going to talk more about the package and environment management in the afternoon's open source session. And Gary will actually show some more examples, I think. But I also share some experience too. There's another question in the chat, actually. I want to address that. So are you using REST API for the Tempest UI? The answer is really no. So the Tempest UI or the Scoped Gateway is really a web portal for people to access the HPC resources without really knowing much, right? It's really like a clicking, GUI interface to give people access to the community containers. Okay. Yeah.
It's maybe a naive question. So if I'm correct, we need to for GPU support, we need to install the same CUDA version.
Yes.
In both the container and the operation system.
Yes. So inside the container, you will need to have, well, I wouldn't say same, I would say compatible. But well, I mean, how you define compatible, the same will be the best. Usually that definitely works. But sometimes a minor version change is not a problem too.
Okay.
Yeah. Tables.
Questions. Would you recommend containerize the software for standing our something? Should we provide the course in containerize?
Yeah, that's some people are already doing that actually. People would think, container is a way to save the, reproducibility prices for science. But I guess part of it is that container is a tool. You want to realize that container itself will not solve any problems. It's really the user, the developer, the scientist who are actually making the data, the software need to address that, right? You can make like a shitty container that no one else can use, and then it doesn't help reproducibility at all. Yeah, right. But it definitely helps, right? So now you actually have a sealed environment which is containerized. Then it's much better than if you just define a bunch of like a makefile or conda definition for the environment, which is not necessarily as isolated as if you're using the Docker container. So yes, it's definitely a really valuable tool to help with the reproducibility.
Container is a tool for reproducibility. It's a lot bigger deal because you freeze the entire environment. It's like if you produce something now, you think about trying with the same software in 2 years will not work at all. But if you have the containerized version of it, at least you have hope.
Yeah, that's true, actually. That's definitely true.
So thank you so much. I want to continue on containers. Lunch is getting ready to be served. And you may want to take it outside if you want to take some fresh air. And so when they're finished setting it up, they're so quiet. It's actually been wonderful. Then you can start helping yourself for lunch. I did have a question about containerization because we have the template from Scoped.
Mhm.
But if I start with a GitHub that's already with my clean environment, how do I go from a GitHub to a container?
Well, so you can always use the from clause in the Docker file to build from the base container instead of relying on the template that I just pointed you at, right? So basically, if you have an existing container environment, most often you can replace your from line with the container base, the site scope container base, and it should work. But maybe you need to make some modifications, of course, depending on what the original base container you are using.
Can I ask you a really simple question? Like, do we add a Docker file to our GitHub repository?
Yes, you can do that.
And where can we find a template of that Docker file? And what should we add if we already have a repository?
Actually, online persons think that they cannot use this.
Yeah, we kind of know that because that oil that doesn't work. The oil doesn't work. Yeah. Only my laptop's microphone is working, so it cannot pick up the whole room.
Something on the microphone while you remove the sound from your computer.
But then nobody can type.
Yeah, but just one.
Yeah, I can repeat the question.
My question?
Oh, okay.
I can.
You can repeat it.
My question was, how do we start from scratch if we already have a clean GitHub that has a clean environment? What are the simple steps to take to containerize?
Mhm.
So we can add a Docker file that we can borrow from the SciScope container
Yes,
base,
yes.
which we can start from the container base and build on top some layers.
Mhm.
Do we need GitHub actions to actually build the container?
Yes. So, well, but that's the thing, right? So if you want to create a GitHub action on your own repository, then you just have to do it by yourself. But still, you can use the template I'm pointing you at and look at the workflow defined in that template, and make changes there, of course, to fit in the directory structure or the specific purpose of your own repository. But then you can just start from there. You will not really start from nothing, at least. But on the other hand, if you are maintaining a repository, I hope you are knowledgeable enough to actually use the GitHub tools to actually achieve any of that without really relying on, the pre-created template, right? So, yeah, but that's actually the difficulty. Well, I do want to talk about that as part of the conversation, As good as it sounds, the container, there are a lot of caveats and pitfalls, which is, it's not that easy to manage. And especially I can give you an example, okay? So if you have code A and code B, okay? It's fine to containerize A, it's fine to containerize B, and they work perfectly well by themselves. But now if you have a workflow that actually runs with A and then runs with B, what are you gonna do? You want to put the two inside another new container? You can do that, but that seems a waste of effort, right? Now you have 3 different containers. One is A, one is B, one is A plus B. But you can, well, sometimes it might be easy to just say, okay, I just process data with container A, save the output, and then processes the output from container A with the container B, right? Well, that still works, but it depends on your workflow, right? Your workflow can be really complicated. And in that case, this model doesn't work well. And it kind of violates the idea of having a completely isolated and strictly defined environment using the containers. Now you have multiple containers, you have script to handle which container runs first, which container runs second, whatsoever. And that's actually a big problem. That's called the interoperability of the containers. And containers is not very good in that aspect. So still, we are not really done yet in this larger topic of reproducibility. Container is a good tool, but it's not going to solve all the problems. The interoperability problem is not going to be solved with containers. And in fact, it's actually going to be really challenging to do that with container. Okay, just be aware of that. Oh, we are past the hour anyway. It's lunchtime. For online folks, I think we're gonna gather in an hour. Okay, so an hour from now. Signing off.
Not forever, but I want to start with kind of a definition about research computing, because I think it's really important to understand research computing and the history of how we got here from this old guy's perspective. And then I'm going to go tell you a story about a particular example I've been working on for the last couple of years, so it's current. And there's a real reason for that, because I learned a long time ago in educational theory that humans understand stories better than being lectured to. So I'm going to try to treat this, it's not like a fiction story, but at least I'll give you a story about how I did a particular thing, and maybe it'll teach you a lesson about the process. That's all I want to talk about is the process, not the nuts and bolts. Ian's going to do the nuts and bolts about some open source software when I'm done here, if I ever shut up. So, come on. See, I don't know the technology, right? See, why will this not advance? There it went. Okay. So, I want to start with this thing about research computing. I think you need to understand that software today is a continuum from on the left, which we'll call enterprise computing, to the right, which is research computing. And by enterprise software, I mean things like seismic reflection processing, an industrial strength piece of processing code that people use to process oil seismic reflection data. Things like a package called Antelope, a real-time system, or many generic commercial packages. They have to work 24/7. They have to always work. There's a hell of a lot of engineering goes into an enterprise class piece of software. The other end of the continuum, which you work one way or another, there it is research software. Most of us work in. The other extreme is you start from scratch. And one of the perspectives is, when I first started this stuff back in the dark ages, this was not nearly as complex as it is now. There was all one thing you do. You wrote a Fortran program. Now it's this complex mix of bringing in things from here and there and all over. Say, how am I going to solve this problem? So most things are kind of in this middle somewhere. I'll call the dusty deck problem. You got a little piece from here, a little piece from your advisor gives you this old piece of Fortran code. It's like, what the hell am I going to do with this? And try to hack it into something, and you got to make it into something useful. And that's the environment you need to recognize you operate in today. And so there's a few things you should recognize about that over this history, is that a lot of the things you get are really wrong because they make intrinsic assumptions that were made 40 years ago, which are no longer valid. And you have to think about, is that true or not? Should I just start over? Is this really the right way to solve this problem? And the other one is that there are open source tools to do things today that just didn't exist 20 years ago. And so you have to kind of go through this design phase about what am I going to use and what am I going to reuse or not do. So here's some just words up here. I'm not going to read through this stuff, but basically the advice is, if you got some solution that does most of your problem, this enterprise class solution, use it. So if you're doing something like, if you work with a network data and you have something like Antelope, or what's the other thing, that solves that problem, do it. But you might have to develop some other pieces to work the workflow together to make it work. Causes some problems about reproducibility if somebody doesn't have a license for that package. That's part of this open source problem, that we have to be careful about commercial products, commercial software that not everyone has. So consider that when you do something like that. And there's just some general advice about how you solve, that's just kind of some general stuff there for the record here on this thing. So why does this thing not work consistently? There we go. So the next part of the story is an example I'm going to tell you about. I've been working on it for the last couple of years. It's just, like I say, it's a good story to tell because it's current. It isn't something I did 50 years ago, which would be totally archaic because the way the rules you run on them were very different. So again, the lesson is in the science, not about the science, but it's the process that I went through to do this problem. Okay, but here's the science problem I had. If you look at, it's sometimes called the Earth hum. This is from a student of mine, my last PhD student named Ross Caton. A couple from his paper, his paper that has been published. Let me point here. These are pre-oscillation lines in this data. There's a difference about these two spectrum of how you process them. So this is frequency. You can see the individual pre-oscillation lines. But there's a band in here for about 1,000 to 2,000 microhertz. That's kind of the unexplored realm of seismology. It's above the pre-oscillation band, but below the tides. And the question is there signal in there? And there's been this series of papers done, actually, that he was inspired by my good buddy Frank Vernon and David Thompson did a series of papers like this. They show that you had these statistical arguments. You can say you see these lines of the spectrum that are weird out in this band, they're like 1,400 microhertz, which is below the gravest free oscillation. But they're pure harmonics. They appear to be pure harmonics that have the duration of months long. Their argument has been that it's free oscillation modes of the sun that modulate the solar wind and create their known lines like we saw the aurora last week or 2 weeks ago, whatever it was. That the sun's output of those charged particles is modulated. And it is the hypothesis is that goes into the couples into the solar wind and then couples into the Earth's magnetosphere and somehow produces ground motion. And this is a real signal. Okay. It's been controversial because it's really ratty about how you do this. Okay. So that's just some words about it. I wanted to go back and say it's the reproducibility question. It's like, Ross, I want to question how you did this. I really want to understand this. Once I'm a retired professor, I got time to work on this problem, right? I want to ask the question right? And so it led me to question some things about this. And the specific hypothesis I wanted to test was this. The data where he was working on was from this experiment we did at Homestake Mine, this fabulous data. These are the tidal lines in this data. They have a signal to noise ratio of like 10,000 to 1. And this data is super quiet at long periods because it's in a mine. And the hypothesis I had was is this an artifact of the way you did the processing? And the particular thing I was worried about is illustrated, I hope if I can get it up here in the next slide. A particular nonlinear filter they used to get rid of transients like this one, mass recenter. He used this long-term STA, LTA kind of transient smoothing filter to remove transients. And so the example was started out with that monstrosity, which had like 80,000 size and reduces down to this. But what that really does is an editing step. And the question is, the issue was this a fundamental theorem from spectral analysis, which is that's actually a window that you apply to the spectrum, whether you knew it or not. And that is to change that, to remove that transient, you had to carve it out and put something else back in there. And the question is, what did you do to the spectrum to do that? And the thing I was suggesting, I've been chasing for a long time now, is that it was a cause of spectral leakage. And so the fundamental theorem, if you've had signal processing, you know that windowing in time is convolution in the frequency domain. So if you apply a window like that, you're going to convolve the spectrum with a window and the trouble with the transient filter and that kind of implementation is you don't exactly know what it is. Okay, anyway, that's to tell you this science problem I'm facing. I want to just kind of, that's not, I'm going to skip through this, I think. That's just a figure to talk about what I just said. Here's an example just to show you the, from one algorithm, which I did with simple MATLAB or Python graphics, is that this is something to worry about. Okay, that's a kind of one extreme window function I got, which was kind of a robust estimator thing, which is really ragged. And basically the power spectrum of that is really bad, really subject to really bad spectral leakage. Now we can do better than that, but anyway, here's this. That's not really the point. I'm not done with this problem, but I want you to understand that was the problem I'm chasing. And it's a geeky data-oriented problem because it's really hyper focused on a detail of the way this algorithm, what you're doing, okay? So the bottom line is, I don't think we can really reject this hypothesis yet. I'm still working on the problem, but I want to go through the process. Some of the things I went through just to give you how complex this turned into, and but at the process. So here's what probably I should just leave it at this. That's all the Jupyter notebooks I generated. That's only part of them. In the last couple of years, playing on this with this problem off and on for the last couple of years, of different things that I tried. And none of them I'm totally happy with. Yeah. The problem I'm dealing with is these kinds of glitches. You probably have all seen them. Transient glitches. There's two kinds of this data. A lot of data, it's hard to see them because they're hidden by the other noise in the signal. You should look at the scale of this. That's about 10 minutes. So what happens is you get a really strong tilt signal, you get a tilt transient, and you'll get this big, looks like a Cal pulse on the horizontals. You can also get these weird three component pings. Sensors will do sometimes on broadband sensors. They're the known instrument problem with broadband sensors. They do these little, they call them pings because they just echo across all the components. It isn't really, nobody really knows what they are. They're probably something in the springs of the sensor. But anyway, they produce a lot of signals. A lot of data, you would never see them. But on data like this, it's super quiet at these long periods. These things are huge. They completely dominate the spectrum if you don't do something with them. And that's why Ross was doing this transient filter thing. And he was automatically editing them out. So the lesson is, there's a lesson to everybody about automated algorithms. Be sure you know what you're doing. Because sometimes you can do things that could be, you're never sure what you did to it, right? So anyway, what am I doing? I'm doing fine. One of the things I tried, these are just words, you go back and look at these later when I post this, but several things using a bunch of techniques called robust estimators. The details are irrelevant. What I wanted for this session, what's important is some of the things I had to use to do it. So one of the ways I did this, since I was one of the developers of BizPass, it was the core thing I used for it, and it was essential to this. It's why I made more progress than Ross. But in the process, I got put in Herman. I started playing with Herman Prieto's multi-paper code. That's a one open source package. NumPy, SciPy, pieces of NumPy and SciPy. Matplotlib, those are all open source packages. And Jupyter, everything was done on Jupyter notebooks. And all these required me to do little custom Python codes to do it. That's you saw my list of notebooks, okay? There we go. That didn't really work. None of those worked very well. So I tried a different thing. So well, I'm going to try manually editing. I did a little gizmo with Antelope to pick. Antelope has a really good manual picker. So I said, I'm going to do this by brute force. I'm going to go through and find every one of those tilt transients and every one of those pings, and I'm going to look at every one of these diagrams. I'm going to know what the hell I'm doing, right? And so I picked windows and all of them and say, okay, now at least I know where they are. Okay. That presented an interesting data management problem because I had to actually develop a new, we'll talk about that on Thursday. I wrote an added on database table, not table, a collection in MongoDB for those intervals. So I stored in the database about a few thousand picks that I made that were different kind of pick than a normal time pick. They were interval picks, but they were just for this algorithm. And it was easy to do that with MongoDB, by the way. And so I should have added MongoDB. That's one of the things I use for this. Use MissPass, but MissPass uses MongoDB internally. Use NumPy, MATLAB, JupperLab, and I used Antelope, which is not open source, but in the US community at least, anyone can get a license. It's a problem internationally, but my result actually does not depend upon, anything I do is not going to depend on that, because I could reduce, the lesson is that I can reduce Antelope's dependency down to something I could produce with this paper, which is the intervals I picked if I end up needing to use that. See what I mean? So I could divorce, it's important if you use, it's okay to use a commercial package as long as it's reproducible. And in this case, it is reproducible because I can publish the collection of all the picks that I made. Anyway, so a couple side benefits of that to you as a community was I developed as a result of it a new part of MissPass called a Datascope, with a long name for a class name, but Datascope database, which is basically a way to read the data tables. If you have Antelope at your institution or have a license for it, if you produce these tables that are used in Antelope for the database, we can read them native now in MissPass. You can load one in as what's called a data frame. We ended up putting Herman's package into the container for MissPass because it was useful to have it in the package anyway. Anybody doing seismology probably wants to do some form of spectral analysis, so it makes sense to add it to the distribution. And of course, I found a bunch of bugs in our own stuff. So there's this natural feedback between working on a package and using it that goes into the open source, that makes the open source package better. And that's the next thing that's the main thing I want to focus on. That's pretty much the last lesson about this, which is my story demonstrates to you how an individual's work can contribute to an open source package. And that is that can improve the fact that I did this stuff. I found some things that added, so I was able to add some things to MissPass that weren't there before. And that's an important lesson for any of you about working with open source tools, is that you need to be able to contribute it back to the community. If you find something that's useful to add back into it, do it, because that's the way that we're going to move the community as a group along and not hoard our own intellectual stuff. So the other part of the list, and the last part of the story, I guess I'm not done with the story yet, that's right, is another lesson. And part of the where I am in this problem right now is I thought, well, one of my co-authors suggested, well, I've heard of these people doing these so-called auto-regressive tools you could do a gap fill. And they exist. I can show you that link. You can follow that link. There's an autoregressive, what you do is you can do an autoregressive or an autoregressive moving average filter that's a predictor from the left and a predictor from the right for a gap. And then it resolves them. There's a way to do it to make them resolve into a single filter that you average them together somehow as you cross the gap. Here's the problem I ran into. I could not make it work. First of all, I couldn't understand how it worked. If you go to the documentation, and I could not make them work with this data. And so I finally said, let me stand back and do it myself. And I'm gonna give you, I don't think I'm gonna give you, did I have another page on that? Maybe I do. Yeah, I'm not gonna tell you how I did it. I did this weird geeky thing with an inversion method. It's still a work in progress, where I basically fit harmonics on the left and harmonics. It's really what the autoaggressive filter does, is I just window around the data and do a DFT across the gap and do solve for the harmonics that match the gap and match it's a work in progress. It's promising. And if it works, I'll put it in this pass, but that's the side issue, okay? The lesson is kind of, I just redid it myself, and that's my decision, the way you do work sometimes. I wrote a lot of stuff from scratch, so it was sensible for me to do that. For you, it might have been more sense to work on that statistical module. But anyway, the lesson, that's important here is about documentation. Most of it sucks in open source tools. You got to realize that. And there's a lot of basic reasons for it. And that is that even the best community software has problems, because most of the documentation was written by the developers who don't know the community that they're always talking to. And so often it's like, what the hell is this guy talking about? It's like, he's speaking Greek, right? I don't know what this means, right? So you got to dig through a bunch of other sources. And that's often necessary. You're just going to have to understand the problem. But that's the point, is that what you need, don't expect to be spoon-fed in the open source world, because the developers rarely have the motivation to actually do the documentation right. So a couple other things there, but anyway, the other one is, if you figure out how to use something, usually you're in a research group that's doing something similar. It would be nice to your fellows and write it up, or tell them what you learned. May not be a published paper or whatever, but somehow it's part of. There are ways now the NSF is getting to be able to credit that kind of thing, about make a page that's a contribution for how to make a website on how to run Gizmo X. And it'll help your community. So when somebody Googles, how do I run Gizmo X? They come up with something they can read, instead of like, huh? What does that say? So that's an important lesson about documentation in open source packages. So anyway, I guess my own preaching about this past, a lot of it went into that. So I'm actually done 5 minutes early, Ian. So that's good, because you want to take more time on, but I'll take, maybe people want to, I don't need to read that. Anybody have any questions or comments, maybe before Ian's coming up?
Questions for Gary?
Yeah.
Perfect time to do them.
Uh-huh. No, it's not. First, the question, how big is the signal? Yeah. What's kind of weird about these, realize is there's a subtlety of the analysis too, which is you're analyzing like 3 months of data per hour. There are a lot of hour periods in 3 months. And so there's a square of noise and noise reduction. These harmonics, if they're present all the time, they come up on so it's the reason that they curse, not because they're endurance magnetic storm. It's like they're already there. That's a hypothesis. And so that's the only reason they were here is that there's always, there's something kind of resonance, something in the system that makes them always there. If it's real. Sorry.
Well, kind of off the topic, I guess.
Yeah.
Sure.
Reward for recognition rating and no recognition. All you get is these.
So yeah. The question was about, or statement was that there's no reward for people doing open source software, right? That is super true. But the only way, there's two things that are going to change that. There are some things changing. Something that's dramatically changed in the last decade or so is that NSF, for example, now explicitly talks about credit for things like websites and so on. And there's a much greater emphasis in most universities about in tenure and promotion about, products that you have outside of traditional paper publications. So it's changing, but the only way it's going to change, it's going to be slow to change. But it's definitely the negative on this, but I think it's got to change. Or it's been a horrible barrier to progress in our field. I guess I should.
No, we are actually gonna touch more on that topic too. I mean, I guess there's no solution, right? I guess that's the problem. But anyway, well, before I start, I have to say, it's lucky for me to have Gary there. Since, just look at the title, open source landscape. How am I qualified to do that, right? It's my age, but with Gary here, he starts. We all can learn from his experience of more than 50 years of software development and actually doing the open source development, open source science, open source software. So you kind of know, how it actually looks like. And you probably already start thinking, all these lessons that Gary learned, and he actually posted, right? The documentation issue, how are you going to contribute back to the open source community? As a developer, how do you want to, show your community how you publicize your work, all that sort of things. Anyway, those are really good thinking, and I actually want to keep the discussion going after my short session here. But here I actually want to start with something a little bit different. Like Gary said, the nitty-gritty details of open source software or how you use open source software, right? These you may all seem very familiar. This is actually the step to install, what is it? OpsPy, actually. So if you just start from scratch on the Ubuntu system and you want to install OpsPy, you probably need to run every single step of these, right? But just looking at that, it's not, well, I mean, that seems really normal enough, like what's special about it? But I do want to think about it, like what's behind each line of that? Like, why do we even need to do that, right? So we have the apt install. Well, we install Python, we install some, dependency like GCC, libffi, whatsoever. Those are the OpsPy's dependencies, right? We actually use git clone to get OpsPy source code. And then we actually use the Python venv to define a clean Python environment, right? Then we activate that environment. We use the pip command to install the setup tools. Then we use another pip command to install the requirements or the dependency of the OpsPy package. Then we can finally do another pip install of the OpsPy, right? If you ever do it from the source code, that's how you do it. Okay, so you kind of see, all the things that appear there, apt, git, venv of Python, pip. What are they? These are actually the tools that I say, will actually help you manage the package and environments. That's actually what's really behind all these commands, right? You actually want to manage the dependency packages of a certain software. You actually want to manage the actual environment your software is going to run in. And that's why you need to go through all of that. You're actually building up the package dependencies. You are building up the runtime environment for the package, okay? So, you know, yeah. You probably already figured that's actually a ChatGPT generated image, but that's pretty nice, right? So without managing the packages or environment, you know, you just end up facing a lot of stuff and, you know, conflicts, everything, and it just wouldn't work, right? So the idea is we actually want to ease the development and deployment, right? So to do that, we use all these automated tools or standardized procedures, right? By automated tools, I mean the APT, I mean pip, I mean Git. These tools, I mean, it actually does a lot of things behind the scene, but for you, it's really just one single command. And that actually helps you either pull the package or build a package, right? But also we want the standardized procedures, right? If you think about it, you know, there are actually a lot of different ways you can install OpsPy. What I show you is really compiling it from the source code. You know, we are actually pulling the OpsPy's GitHub repository. But you can also just do it with pip install OpsPy. You're actually pulling it from the Python package index, right? You can also do a conda install OpsPy, which is actually pulling it from Anaconda's repository. These are different ways to do it, but they are all standardized ways, right? So you can actually see, you know, it's important to have the steps standardized. So the environment or the packages you get is actually well controlled, right? And the other reason we want to manage the packages and environments is really to facilitate the collaboration, okay? So with all these tools, these commands, we now actually can have like a common ground, like where user will start from, right? So for example, for the OpsPy developer, they can say, okay, once you do the apt install Python 3, GCC, libffi, whatsoever, you know, once you have all those commands run, you will actually have the environment set up to actually get OpsPy installed, right? So really, it's actually setting up the common ground for you, right? And of course, we need documentation. We need virtual control systems to actually further set that up so someone else can, you know, reproduce the work, right? Given instructions, like Gary just showed. Yeah, and the most important part is we want to avoid the dependency conflicts. That's the whole reason we want to do that, right? Especially, you know, if we do like a Python vin, we probably have different Python environments. We want to create a specific version of Python. We do that, and people use virtual in for the same reason, right? So we can have different Python virtual environments. Each will actually have different Python packages in it. So we want to create that to have isolated environments. And in addition, you know, the container we just talked about this morning have the same aspect, right? It's an even more isolated environment such that, you know, only the tools, the packages you define, you installed inside the container exist. You will be confident that there won't be any conflicts, right? So that's important, right? And then it actually ensures the consistency, right? So I just show you those commands running from Ubuntu, and it probably works fine within different versions of Ubuntu. But then if you're on the CentOS, well, the pip commands, the Python related commands still works. But then to install the dependency packages, you won't be able to use apt. You will need to be used, you know, the yum command, right, or the dnf command, if you are familiar with CentOS. Okay. And most importantly, we want all of that for reproducibility. These are actually part of the reproducibility. We need to have a way to control the packages, to manage the packages, the environment, to be able to reproduce the work, right? So, package management, okay? That's the definition I got. Doesn't matter, right? But I actually highlighted the keywords. So for package management tools, it needs to be automated, right? And it actually needs to be able to install, upgrade, configure, or remove packages in a consistent manner, okay? So if you think about it, this definition is actually very broad, It actually covers a lot of tools, which I'm going to show next, right? So you can actually see the common challenges that we are trying to address with these tools, right? Dependency issues, version conflicts. Well, also there's the package overhead, right? So sometimes you actually have unused packages, outdated packages. You want to be able to remove them. So not just installing it, right? Removing is also a process that needs to be standardized and made consistent. And there's the interoperability issues, which I actually touched on this morning at the end of the container session, right? Different versions of the same thing, or you actually have 2 or 3 different software that you want to use together. How to make them interoperable. That's also challenging. And I wouldn't say all these tools solve all these problems. You can actually see some tools will actually try to address some of the issues, but not all of them. And that's the normal case, right? So, well, I was gonna do this, but that's not necessary. But with that said, I want to be able to recognize these are the common package managers, okay? So you actually kind of see what I'm getting at. I want to start from a very different perspective, okay? So, if I go through all this list of packages, you would just think, well, they're random, right? Like apt is for Ubuntu, ENF is for Red Hat or for CentOS, kind of Linux system, right? Conda is for Python. They are kind of unrelated, but they are because they are all trying to achieve the same thing, which is managing the packages. And if you get that, you will actually see, all these things are just doing the same thing, but just on different systems, on different environments, or for different, software languages or whatsoever. But they are actually the same thing. Well, of course, Git is a little bit different, right? So Git, people will think of it as like a version control system, but if you think about it, it's actually still a package manager if you think about your source code, the text files, as packages, right? It's really just a finer grained way to control your packages, right? And there are actually many more of that, of course, right? Like Homebrew, if you're using a Mac, you probably cannot live with that tool. Otherwise, you can't really do anything, right? Chocolatey is a Windows variant that also does the package management. There's a Nix, which I can have a completely different talk on that, but Nix is a very interesting package by itself. Anyway, not very important, right? With the package manager being all set, now we can talk about. Next thing is actually managing the runtime environment. And you should recognize it's actually different than managing the package alone. Because by managing packages, right, you are really just managing the packages needed. But at runtime, some of those packages may not be needed. You may just need to use that package when compiling a certain software. But after it's being compiled, you no longer need that. So that's not really going to be included inside the runtime environment. This is the definition, again, not going to read it. But what this runtime environment management trying to address is really, dependency management, change of configurations, which is actually important, right? Even if you have the same package installed, you might need a different configuration for different workflow, different problems you are working on. That needs to be addressed, right? And also, one thing that a lot of people will ignore is actually the scaling issue, which is, if you have an environment set up on your local machine, a laptop, how are you going to use it on another laptop, right? On your desktop. Or if you have your environment set up on the login node of your HPC system, how are you going to use the same environment on the compute node? Especially if you are running large scale simulation on hundreds of nodes, you can think each node is actually independent. And there has to be a way to manage the environment of each compute node independently to make them consistent. And that's also part of the environment management, right? So if you have that in mind, you will now see, these tools are pretty much doing the same thing. Although on the very, very surface, they might just appear as tools that's very different and not related at all. But if you think about it, they can all achieve the same thing, which is managing the runtime environment. And that's important, right? And I'm not going to go through all of them. So I think the idea is I'm going to list this, and you can just Google them. If you don't know one of them, and you definitely want to Google them, understand what they can be used for, and you will usually find really good documentation on these tools, because these are really popular open source tools that's used by the community, not just our seismology community. It's really for the whole community, the open software community, right? Okay. So with all of that being said, I think now you kind of have the same mindset of what packages are, what environments is, and now you kind of understand, okay, all of these open source tools are really just doing two different things for you: managing the packages, managing your environments, right? Which we all like as scientists, because now we got things simplified and we actually have everything like in a common aspect, which is not important, okay? So I listed a few best practices, right? So you want to be able to leverage all these nice tools to help you manage your packages, your environment, right? So for example, you want to use Git to manage any text-based content. And always you want to start something from a controlled context, meaning that whenever you start working on the project, you want to start with thinking of the package management and environment management in mind, such that you actually start something with a very controlled context. And later on, it actually helps with the reproducibility problem, right? Because now you start with something that's well managed, you can easily make others to replicate the same environment that you actually started with. And that's actually important. And that's also what's been lacking in a lot of the projects. These environments or package management are mostly done after the fact, right? So now I've got my paper published, someone else is asking me this question like, oh, I want to use your code whatsoever. Now I try to, okay, make up the documentation and say, oh, you need to install this, install that. Now my code should work. Most of the time it wouldn't work because you didn't really start having all these different elements in mind. So that's important, especially for you if you are starting early in your career. Very important, okay? So yeah, even if with those tools, you can see those are different tools. So you still need to automate the process to coordinate different tools, right? Like APT for managing the Ubuntu's environment, pip or conda for managing the Python environment, the virtual env command whatsoever, you still need to be able to automate the process. Container is definitely a way to automate it if you have like a container file, a Docker file, so that you can define exactly the steps to replicate the environment or packages needed for the project, right? Yeah, Gary already mentioned that, right? Always keep documentation. I know it's difficult, but I hope, if you start with something well controlled, it wouldn't be that difficult to actually document everything you did, right? Especially if you have the tools, rather than relying on some custom scripts that does different things in a non-consistent way, not using the proper package or environment manager. Then yeah, it will be more challenging to keep the documentations, right? And last is choose the right tool for your project. And that's something I can't really give much advice about because, there are just so many tools out there. And that's actually what I feel challenging for this topic, because I just can't list every single tools out there. And even for me, I'm not really experienced enough to know everything, right? Not even Gary. I mean, Gary had 50 years of experience, but still, he only used a limited number of tools. And that's true for every single one of us. But that's fine, right? When you start something, you can always Google it. And there are always some really nice tools out there and with documentations. So use them, adopt them, okay? That's about the package managing. The last subject I'm going to talk about is actually how to contribute to the open source project, which is also something that Gary touched on, right? So I hope after Gary's talk, you kind of understand like what open source project entails, right? Like from the user standpoint, how you may use them, from the developer standpoint, how you want to share them to the community, you know. And it's quite interesting that, you know, although we switch between the two different identities all the time, you know, sometimes we are user to a certain packages, sometimes we are developers of our own packages. We didn't realize the fact that, you know, these are people of two very different mindsets. We can talk more on that later, I guess. Okay. I don't want to read this actually, but basically this is the process of contributing to an open source project on, you know, GitHub or GitLab or whatever, like open platforms out there, right? So start with reading the documentation, which is important, right? Without reading the documentation, you might be just working on something that the developer already implemented, you just don't know. Use the communication channels. So I know this is something, you know, the developer may not set up for you, but usually you can use the discussion page or the issue page inside the GitHub repository, okay, to communicate with the developer. Because, you know, if you want to propose some new functionality of a package, you know, you want to propose it first without just directly start working on it, right? And later on realize, oh, this is not really what the developer wants, or maybe the developer already is working on that, and you just duplicated the effort. Yeah, and then, you know, with the documentation, with the communication, the goal is to learn about the coding standard, the testing procedure, every single, you know, nitty-gritty details of the project that you do want to contribute to, okay? After all of that being done, now you can actually start, you know, trying to improve the code, the open source code, and then open a pull request, submit it, you know, let the maintainer or developer to review it and wait it to be merged. That's really the very simplified workflow, okay? But, well, I think some of you may already know that, but I do want to point out some best practices, okay? Yeah, let's do that. So first thing is be patient, okay? Developers probably don't really have the time for you, right? So they may not review your code. They may ignore your request, and that's normal. And you need to think about it from a developer's point of view. Like if you maintain your own package, you publish something, you hope the community will use it, right? Then you actually start working on your paper or your next project. And then someone else come up to you, like say, oh yeah, this thing is wrong, you need to do that. Oh, we need to implement this. You will probably just ignore them, right? Because, I mean, why? I already published my paper. I even published my code. Come on, you can just do it yourself. And that's the really typical mindset of a developer, right? So if you are a user, you need to be aware of that. Just, you know, wearing your developer hat, and then you understand why you need to be patient and persistent. Because, you know, developers may not, okay? And you also want to engage with the community. You want to talk to the people who actually maintains the code, who actually develops the code, because, you know, without staying involved in the discussions, you might just duplicate the efforts. And also, once you get engaged, you can actually start collaborating with them by offering the helps that they might need, right? That's actually important. But in the end, you also need to respect the community's decision, meaning that if your idea is being rejected by the developer, well, don't feel upset because it's normal, right? Just again, think from the developer's standpoint, right? Someone proposed something, but then, you know, if you know the science problem really well, you will say, oh, this algorithm just make no sense. Just don't waste your time on that. And that makes sense, right? Then as a user, you know, if your idea is being rejected, don't feel frustrated. You know, there must be a reason that a developer, you know, would make that decision. And that's also why, you know, engaging with the community and communication is actually important. The last thing is, and that's actually the most important part, you don't have to contribute code. Just think about it, right? As Gary mentioned, for example, you know, you can even just contribute to the documentation. If you, you know, use this open source package and you know, run into some issues, but then you eventually figure it out, you may just want to add a few lines to the documentation so that the next person won't run into the same problem that you run into and wasted maybe 2 days to figure out. And that's actually important. Okay, you can contribute to examples, okay, notebooks or tutorials, presentations like what I'm doing, whatever, in different conferences or workshops showing how the code is being used. And that's actually a huge contribution to the code, apart from just contributing the code itself, right? You can even just go through the open issues in the repository, right? And you can try to help organize them, mark the ones that's out of date, mark the ones that's actually duplicated. It actually helps a lot to the developer. And if you are a developer of an open source package, you would realize that, right? Sometimes people just open an issue, and then you realize, oh, this issue is being opened for like 3 days ago by another person. Why don't they read that? It happens a lot, right? And from the user's point of view, it's normal because you don't have the time to read all the documentation. You don't have the time to read through all the issue page. And maybe when you search through the issues, you are not using the right keywords. So even there's another issue page that's been submitted by someone of the same problem, you may not found it previously. So you open a duplicate one. It happens a lot. So as a user, you can actually contribute by organizing them. It actually helps a lot, right? And inside the open issues, you can also help answer questions. Like if you know this open source software, better than the person who actually opened the issue, you may want to offer some help. And that's contribution, actually. That's actually also a significant contribution to the community, because if you think about it, if you think the community as only the developers, well, usually a package is only developed by like one person. And that's probably most of the case in seismology, right? And one person doesn't make a community. It's really the users plus the developer that actually makes the community. So if you use the package, you are actually part of the community. Then, within the community, you can help the others, the latecomers that might have, issues or like a very simple questions that the developer just don't really have the time to answer. And maybe he already answered like 10 million times of this same super simple questions. They don't really want to do it. And you can help with that, right? So with that being said, I actually want to conclude this session, okay? So I hope I already give you some very different perspective on what open source projects are, open source tools are, right? And any questions? Anything you want to mention? Or we can start a discussion on what you think we can do to the community, what you think, how we may use these different open source tools for the 5 minutes. I don't know. Any questions? Carl?
You were saying get in the head of developers, trying to get in the head of students, users, right? Just on the end of incentive structure, I don't think, certain issues are very helpful to document. You may be the only one who's really dived into a problem to document something. It's an extra effort to write an issue that's going to be public and on the internet forever. And so you may feel like, I don't want to go there. But if you do that on the side of, someone writing a letter of reference for you, you may think that sounds minor, but I can tell you for sure, I can imagine letters I'm going to write to people when postdocs, I'm going to say, they played a vital role in this development. You can find these issues, and you can go find that support directly on the internet. So just think broadly about the impact, and maybe you have to remind your advisor about that contribution later, but that's the kind of thing that, it does have indirect payoff in some cases beyond just the values like that. So well done.
Yeah, definitely. It's always important to switch between the different roles. And, if you can do that, you can actually make sense of a lot of problems or issues inside the community and avoid a lot of, tensions between the developer and the user.
One other comment, in the last couple of years, I'm sure that through that kind of GitHub issue exchange, we've had students save months of effort over just a sharply responded question on a GitHub issue. I'm not exaggerating months of work. So someone just said, hey, did you try that parameter deep in this constants files, and we worked on that. And yeah, so just being involved gives you an edge, because when he says from the developer standpoint, are they gonna respond to you? If you contribute an issue, it's a much higher chance that they're gonna respond. I mean, there's just a certain give and take involved. If all things are equal, you're gonna get better feedback if you sort of helped out and been more careful with.
Yeah.
If we all people out here, focus on software, traditionally as the author, and then the author easy for a long time, and then like where he has already replied on the set issue, or so time to get it forward. And then before there's also more asking questions on the research, and then people are posing questions for the same software in different places, and sometimes we just Google it, but I don't feel like it's sometimes you have to have like a Google algorithm in order to change it, but it's not a very efficient way to discuss like what's actually tailored software problems or issues you imagine in the future, or there's already the
Well, short answer is no. Because it's challenging actually to think about it, right? Because even if you build such a community platform, like even Scope, we are trying to build like a community platform, right? Like how can you attract like the whole community towards it? It's almost impossible actually, I mean, it's possible, I guess, but it's really challenging, I would say. But I think that's a big aspect of the open source community. It's like there's going to be duplicated effort. There's going to be duplicated questions. There's going to be everything duplicated, and it seems wasted. But as a community, if we can all, contribute, as the way I said, not just to the code, you can contribute to the issues, to answer the questions, then, it might just function as a community. And well, think about it this way, not just seismology, right? Just think about how, in general, open source community works, right? There are a lot of great open source tools out there, like PyTorch, for example, like NumPy, for example. These are really well-known open source packages. Do they really have a community? They definitely don't. Definitely not at the very beginning. Well, now they probably do have a community, right? If you post some questions, PyTorch issue page, someone will actually try to answer you. There are probably some what is that, like Slack channels whatsoever, that's available for you to actually directly messaging the developers or users. But those are really big packages. Like those communities are being built up. But you can think at the beginning of these tools, there's definitely no community around, right? So that's the question, right? Like do you want to build a community first, or do you want to build software first, right? And it kind of evolve interleavely, I guess, right? So, the community will actually grow up bigger and bigger with your software being more and more mature. And I think that's probably going to be the model. Although, it seems less efficient, but that's just the way it is, right? We're not really inside the industry where we can just force asking everyone to work on the same project, looking at the same thing. It's just not possible. Okay, well, no more questions. We are at the clock, so I can start the next session, which I'm probably gonna run over. I don't know. I got a lot to fit into this 1 hour. Okay, but before that. Okay. Oh yeah, we don't have like a break time between the 3 sessions in the afternoon, right? Okay.
See how it's.
Maybe we shouldn't play this.
I don't know.
You are dialing?
Yeah, yeah.
Yeah, because I think
On
maybe
the
another
Fairbanks
table
data
that
set,
is maybe another table that we
trying
put
to
here,
detect
so
the
they can see
cars.
more. Hey, on Zoom, can you tell us if you hear better now?
That's
Pretty close.
Yeah.
Yeah, yeah. Oh, yeah, I don't know if it's exactly in Fairbanks, it's on Farmers Loop Road.
Did you went there?
No, no. I just stared at,
Wondering, but we already fixed it, so we use my
5
phone.
minutes of the data for like a year.
The volume very down. Use the headphone. There is no data for you.
Yeah, well, I was just trying to figure out an algorithm
But I have no idea. But if you already got the mic.
to
I will try.
detect the cars.
Okay.
Like figure out,
Okay, that's it.
because hopefully it can be automated.
Okay, okay.
Thank you so much.
Yeah, yeah, it's, especially during like commute hours. You can
Okay.
see some of them that look like they have to be like 18-wheelers or something.
Can distinguish the heavy ones from
Yeah, we can also see like the number of wheels or like how long it lasts in a given location.
Julien?
So,
Oh, he's muted.
and like some of them are narrower, so
Should we
maybe
do
that
two
was a
mics?
motorcycle. Apparently people have been able to like detect the 4 wheels.
Like that?
Cars.
How's that now?
Yeah. But
Now it's good, but
what
can
I'm
you
doing
still hear
there
the
is
room?
just
But
trying
that's
to
gonna echo.
select regions that have higher amplitudes pretty much.
Julien, is this echoey still?
I'm in math, but I have a minor in computer science.
Not so much. Okay, thank you, Rajesh.
Side hustle.
Yeah.
So I just keep this set up?
Yeah. Because we had applied math too, right?
2 minutes?
You're geophysics, but doing the math one.
This one?
Yeah, I'm unmuted. That one is also unmuted.
Okay.
That works better, but I don't know. Okay. Maybe we could get started.
Okay.
I probably won't be able to finish anyway, so we'll see. HPC, supercomputers. So, okay. So this session is really about HPC systems or supercomputers. Okay. So, but I do want to start just to give you like an idea of what supercomputer is. They're super, meaning they're actually super powerful. They have a lot of cores. They can actually achieve high floating point operations per second. Okay. Of course, they actually use a lot of power. You can see, a few tens of thousands of kilowatts. It's actually the current top HPC systems in the world. Okay, which is Frontier. And second one is Aurora, which actually just got submitted their score a week ago on ISC actually. But the machine we'll be using today and throughout the rest of the week is actually Frontera. Well, it actually appears much smaller, but I can tell you, for 5 years ago, I think it was 5 years ago, when it first came online, it actually ranked number 6. Okay, you just can see how fast it drops the ranking because people just keep building more and more larger and larger HPC systems. Okay, and I think last year when I gave this talk, Frontera is at 16 or 19, I forgot. Now it's 33. But we will be building new machines actually, so we will actually have a new machine that has higher ranking. Doesn't matter.
Maybe Ian, just to emphasize on, why some people try to, the science problem should be limited by computing. Like if you're thinking, I can't do this because of computational limits, that should sink in that this machine still has 400,000 cores. And number 6 drops to 33. It's outpacing probably our imagination for scope of the problem.
Yeah, exactly. Also, just to give you a reference scale, okay, well, this is no longer high end, but it's still a pretty good desktop machine nowadays. But the actual, the floating point flops is only 1.6 teraflops. You can see how many orders of magnitude smaller that was compared to real HPC systems. So that's the actual scale we are looking at. Oh, okay, but I need to walk. Okay. Okay. Yeah, it's really echoing for the online folks, I guess. We'll see. Yeah. Well, so it's important to recognize we have these powerful machines, okay? But it's also challenging to utilize all that computing resources, all that computing powers. So hopefully, throughout this week, you actually learn some existing tools, existing applications, seismology applications that can run well on these machines, like SpecFam or SISO. But today's session, I'm really just going to give you a brief intro on what HPC is, how do you do parallel computing, and hopefully we have a little bit of time left to actually log into Frontera and try it out, okay? And I have 70 slides, which I don't think we can go through. But that's okay. HPC systems, so they are really interconnected machines. So at the very early age of HPC, they are really just a bunch of desktops. They are connected through Ethernet, so they can communicate with each other, okay? But nowadays, you actually see this big cadence of machines. They are more dense, consume higher power, better cooling, all that, but it's still the same. You should still think of them as a bunch of interconnected high-end desktops, okay? That's the whole architecture. There's a definition. I'm going to read through them. But I like the second one, actually. Supercomputer is a computing system exhibiting high-end performance capabilities and resource capabilities within practical constraints of technology, cost, power, and reliability. Okay, keep that in mind. The reason we are not building bigger machines is not because we cannot do that. It's because we have the practical constraint of technology, cost, power, and reliability, meaning that technology itself is not really the only constraint. Sometimes it's the cost, sometimes it's the power, sometimes it's the reliability. Okay. So shared memory. Let's start with shared memory first. Okay, so basically, being able to use the HPC system, okay, we need to be able to run different things at the same time. I guess that's the only way to utilize them. But you're probably all familiar with what's being called the shared memory, okay? It's actually like the laptop that you are using. Nowadays, people are using, 4-core, 6-core, 8-cores laptops, right? Pretty common these days. So you have a bunch of cores in your machine, and they are actually all connected to the same bank of memory. Okay, that's what's being called the shared memory, meaning these 8 cores share the same amount of memory. Okay. So the programming challenge here is actually how to avoid competing for access to the same puzzle pieces, the same memory regions in the shared memory. Okay, but that's shared memory programming. So the principal programming model in shared memory is being called OpenMP. Some of you probably already use that. Also, you probably not use OpenMP, but you probably use a threading, right? So you can, use different threads to do the same thing, and each thread will hopefully bind to different cores so that they can do their own computation, right? So a single executable actually spawns independent threads and manages the threads to access data. So you only run one single binary to use the shared memory architecture. In contrast to that, you have the distributed memory. Okay, and that's actually the more important ones in nowadays on HPC system. It's called distributed, right? Meaning that now we have core, or really I should say cores, but that's okay. It's a simplified concept on this distributed memory architecture. So assume we only have one core. Now these cores each have their own memory, but the cores are connected with each other through the network. And that's the typical setup of distributed memory. So the programming challenge here is actually how to share the puzzles or the data, right? Now you can see, every single core will actually see a different region of memory. Now we actually need to use communication to share the data in between them, to coordinate them. So this, the most popular programming model utilizing distributed memory is called MPI, Message Passing Interface, okay? And from the name, you can actually see this is really a library to help us communicate. It's passing messages, right? So in this case, each core will actually run a separate copy of the same executable in this model, okay? And of course, we still need to be able to distinguish them. So we usually assign rank to the different tasks. So we can say, oh, core number 1 runs rank 1, number 2, rank 2, whatever. So that's the typical distributed memory setup. Obviously, nowadays on HPC system, it's neither shared memory nor distributed memory. It's actually more of a hybrid architecture, meaning that we actually have multiple cores within the node, and then we have multiple nodes interconnected through the network, right? So the multiple cores within the same node will actually have shared memory. But then across the network, between different nodes, the memory is distributed. Easy enough, right? I hope. So, there are different things you can do. You can do pure MPI with this hybrid architecture, meaning that I just ignore the shared memory aspect. I just pretend that there's no shared memory. I just treat each core just has its own memory chunk, even if the core is in the same node. Then you can just do pure MPI programming that works, right? We can also do a little bit advanced hybrid programming using MPI and OpenMP, such that we will have MPI to communicate between the different nodes, and within each node, there's going to be only one single process being launched, and that process will actually fork multiple threads, preferably using OpenMP, such that all the cores will be utilized. And then, within each node, they can actually use the shared memory to avoid certain issues or overhead. Okay. But you cannot do pure OpenMP, obviously. Pure OpenMP will only work within the same node, shared memory architecture, okay? So with that understanding of the architecture, now we actually have this hierarchy of parallels being deployed on board the HPC system. So, we have multiple nodes that's actually connected through the network. Right? That's actually called multi-node programming. Within the node, there are actually multiple sockets. So it's not like one single CPU chip. Usually nowadays, HPC systems are using dual socket systems, so there are actually 2 CPU chips, right? So this is multi-socket, and within each socket, there are actually multiple cores in the same chip. So that's the cores. But even within the core, there are actually what's called Intel usually call it hyper-threading, right? It's simultaneous multi-threading, SNT. That's the official name. If you're not really into Intel naming convention, but usually, you know, nowadays the modern CPU cores will actually can simulate two different threads, you know, hyperthreads. So, you know, within each level of parallelism, you can see, you know, there are tricks you can do to optimize your code to do the programming right. But of course, we're not really doing all of that. I just really want to make you aware of the existence of the different levels. And that's actually important when you try to understand the performance of certain thing you are running. The next thing you want to understand is measuring the scalability, okay? So you may think, okay, if I write a code that can leverage distributed memory, then it might just work on hundreds of nodes or thousands of nodes. Well, it's actually not that easy. The ability to scale your code from a single node to multiple nodes is called the scalability. And there's actually certain constraint there. And if we are doing parallel programming, this is actually important. A good analogy we can use is how fast can you bake a cake, okay? So assume, of course, just assuming it, right? It takes 2 hours to prepare the cake for baking, and it takes another half an hour to bake the cake, okay? So it's simple enough, right? To bake a cake, you need 150 minutes, easy. Okay, now, well, there's no parallelism here, right? So now, if we have, you know, 2 cooks, they can just prepare the cake separately, right? And the prepare step is parallelizable. They can do it independently, meaning that with 2 of them, now we can use 60 minutes to prepare the cake, right? But the baking process, well, there's no way to speed it up. You still need to put it all and wait. That's another 30 minutes. So if you sum that up, with 2 cooks, now you can actually bake the same cake with 90 minutes, okay? So if you plot a little bit more data points, you can actually see, let's do that, right? So at the very beginning, it seems, well, you know, you're actually getting a really good parallel efficiency for speed up, right? So with 1 cook, speed up is 1. With 2 cooks, you can achieve 1.7 times speed up. Of course, because of the baking step, the oven step, you still always need to take the 30 minutes, right? So it's not like perfect scaling. But then if you further plot that, you will actually see you have actually diminished return by having more and more cooks. And at the very end, you know, adding more cooks will not help much because now you're completely bound by the 30 minutes time of the baking. And that's actually the constraint of the scalability. In computer science or in HPC, this is called the Armstrong law. Okay, basically, ignore the math here, but basically it's just telling you your parallelism or your scalability is bound by the fraction of your sequential code, the sequential portion of your code. Okay. So now you probably understand why I say you cannot just easily scale your code up from, you know, tens of nodes to hundreds or thousands of nodes. Because before you're doing that, you probably already hit the Armstrong law scalability down. Right, really simple math. Okay. So summary. That's not summary. Yes. Here was we went through all of these topics. Let me skip it. Okay. But always keep in mind, you know, if you want to improve your code's parallelism or scalability, you actually want to reduce the portion of the sequential part. That's actually important, right? With less and less of the code being in sequential, like required to be in sequential, your code can actually scale up to more and more nodes. That's very important. Okay, with that being said, now we can start to learn a bit more about Frontera, which is the system we'll be using in this session, and you know, in the workshops throughout the week. So first, I'm going to introduce the Frontera system and user environment. So, yeah, you see the version no. 2022 is ranked 19. I probably need to update that. Now it's 23. It's funded by NSF. We got 8,000. Actually, now it's actually more than 8,000 because we have some supplement funding to build more nodes during the pandemic. Doesn't matter. It's using the Cascade Lake compute CPUs from Intel with dual socket setup. Each socket has 28 cores, and there's 192 gigs of memory on each node. Whatsoever, doesn't matter. And there are actually 3 different file systems founded on Frontera. So we have the home, we have the work, scratch file systems. Okay, doesn't matter. Okay, so this is how an HPC works. This is important. Okay, so to access the HPC system, you usually SSH from your laptop into the internet and landing on the login node of an HPC system. And usually there's only a small number of login nodes. Like on Frontera, there are only 4 different login nodes. So you will be automatically assigned one of the 4 login nodes. Okay. Once you're on the login nodes, you are on the machine, but you cannot really run anything because this is actually shared node. There are probably another hundreds of users on the same node with you. What you need to do is you need to submit a job, and that job will then be run on the compute node, and that's the more than 8,000 node I'm talking about. And that's how you actually utilize the resource, right? So you actually request for a certain amount of compute nodes in your job script. Then you start running something on the node that you requested, okay? And these compute nodes, including login nodes, are actually connected to the file system, right? So we have home, work, and scratch, okay? To access through SSH, you need to have terminals, right? So, Windows, if you're using newer Windows, you have terminal, Mac has terminal, but there are also third-party SSH applications you can use. You need to set up your MFA. Actually, for all the in-person attendees, I ask you to create your account and set up MFA because those are the prerequisites to be able to access the system. So to log in, and especially for those that already gave me their username, they can already try it now. You just do SSH, your username at Frontera.pack.texas.edu. Either way, this is my username. You don't need that, right? It will ask you for the password and the token. Okay, password is the user password. Token is the MFA thing from your phone. We'll have time for, well, we may not. Yes? Not necessarily right now. I'll leave some time at the end for you to get on to the system. But you can try it now while I'm talking too. I don't want to pause. That's the thing. Or if you have questions. That's okay. Just send me messages on Slack, okay? And I cannot do it now, but it's okay. The exercise I'm going to do today is super simple that you don't necessarily need to do it yourself. I just want to be able to set you up for Wednesday's sessions, which you will be using HPC system for both morning and afternoon, okay? One thing to understand is the user environment, okay? So you have your bash RC or bash as your default shell. So, well, I mean, I hope you are into the Linux world, so you understand what I'm talking about, right? You have the dash RC to set up your environment. You have the paths, you have LD library paths. It's just a Linux system, okay? With all the Linux thing entails. So you can do CD, LS, whatever, okay? Okay, now, important thing. There's an LMOD module on HPC, and that's probably something you're not used to before. The module is the tool that actually manages the environment on HPC system. Remember the environment managing part I talked about in the last session, okay? That's it. That's what the environment management is on HPC system. Basically, you need this command, like module list, to list the available softwares on the system. You can do, well, no. It's a module list to list the modules you are loaded, okay? You can do module avail to look at all the available softwares on the system. You can do module load to load a specific package, like method, okay? You can do module unload. You can see help info, do module oneness, okay? But what's nice about module is that once you got it set up on your logging node, it will work the same on the compute node. So you will actually have the same environment. That's the scale unity I talked about in the past session, okay? Yeah, well, I can go through that. That's okay. You will be able to read the slide afterwards, okay? I don't want you to go through every single thing because we don't have time. This is another user menu type of presentation that I don't think it's worth a while to talk through all of them. Okay. One important part is the good citizenship. Okay. So you actually share Frontera with almost 2,000 other users, okay, all the time. So when you are on logging node, make sure you don't run anything except, editing text files, doing lightweight stuff, like, untar a small package whatsoever, that's okay. But don't run your, large computation, wave simulation, source simulation, whatsoever. None of those should be run on the logging node, okay? File access is also another part, right? So if you run anything that's IO intensive on the shared file system, you may lock up others' access to the file system. So it's important to avoid having too many small files in one direction. Okay, that's just for the sake of how the file system works. With more and more files, small files in one directory, the metadata server will actually have higher load and eventually break the file system, so no one can access it. Okay. And also, if you are accessing external files, make sure you are not doing like a simultaneous file transfer with multi-threading or whatsoever. You don't spin up like a 50 thread, or even using like 100 nodes doing the download. That's not going to work. Job access doesn't matter. I'll skip it. File system. Okay. So on Frontera, there are actually 3 different file systems. We have home, work, and scratch. So home, there's a quota, 25 gig for each user, and a maximum of 400,000 files. And work, we actually have higher quota. Okay, just make sure you don't exceed the quota. Then on Scratch, there's actually no quota, meaning that all your research data that are logged need to be pushed on the Scratch, actually. Okay, only the important ones you put on the home, and make sure you're aware that home is actually the only backed up file system, meaning that if you lost something, you can always ask for it back from the backup through the ticket, of course. Yeah, doesn't matter. Kind of touch on that. This is how the file system get connected. Doesn't matter. Tag info, you can actually see your file system usage using the tag info command. Minor, not important. Heavy IO. Yeah, that's the thing I already talked about, right? So another thing to avoid breaking the file system is to have very heavy IO on the file system. So, here are some examples of intensive IO that could actually affect the file system. You can see. But none of the things we do throughout the week will do that. But then if you're going to use it later. Yes.
This is a new one, 100 gigs per second. This is what the cloud is for, not HPC. But I've run into this issue in my institutional cluster.
Yeah, so that's actually because the file system is actually set up very differently. So on shared system, we are actually using distributed elastic file system, but on the cloud, we're actually using an object store, which actually doesn't have the same metadata requirement. So it wouldn't actually cause the same issue. But anyway, this is what it is right now. well, also I want to say on the next generation file systems, people are actually recognizing the issue, especially for AI workflows. Intensive IO is actually going to be the norm. So, you know, the next generation file system will hopefully address such an issue so that you know, intensive IO will at least not going to break the file system. Right. Okay. Yeah, I'm going to skip this actually, so that you have time to try the hands-on. So yeah, so right now on Frontera, if you have intensive IO, it's better to redirect that to the dash 10, which is just actually the local storage, not being shared, meaning that you can do intensive IO there. That's not a problem. Okay, and because of that, we actually have the Simus IO project, my project, that can actually use the local storage to spin up a temporary file system, not being shared, meaning that we can actually handle intensive IO on HPC. But we don't really need that for next generation, I hope. But we haven't tried it yet. So if you need to transfer your file to HPC, to Frontera, you can use the SCP command or rsync command from your laptop. On Windows, there's the WinSCP. Okay. Also, some people prefer using the Globus to transfer large files. I think probably most of the US institute have the Globus set up. So that one is available as an endpoint on Frontera too. Yeah, doesn't matter. Compiler code. So you're actually going to walk through some compilation later on, if there is any. So, but I'm not really going to focus on it. So you need to load the compiler module. You need to load the MPI module to be able to compile the MPI code or C++, Fortran code you have. There are some different compiler options. We have the Intel compiler. We have the GNU compilers on the system. Yeah, we have 2 different MPI. Let's skip that. This is how you compile your MPI programs, which I think in my hands-on I have. Oh no, I don't have you compile it. Okay. You can read through it later on. Okay. After that being done, you can finally run your program. Okay. So remember, we have a large number of nodes. So you need to submit jobs, and your job will actually go through a job scheduler who got to decide, you know, when to run what job, basically. Okay. Don't run on the login nodes. Again, always submit a job for anything large you're going to run. Yeah, resource manager. Okay, so just want to show you a little bit on how the job scheduler works. So basically, the job scheduler is nothing more fancy than playing a simple Tetris on the system. Okay, so basically, what it does is it just use the y-axis as the number of nodes. Okay, then the x-axis is the time, the time that's requested by the job. In that case, then each job a user submitted can be defined as a block. It uses this many numbers of nodes, and it's going to last that many minutes or hours. Okay. So the job scheduler is really just filling the space with different size of jobs like that. Okay. And you can see, you know, yeah, it's trying to optimize the usage of the resource like that, right?
Ian, why is I've been doing this for 20 years and I've never seen such a nice explanation. Why? Why is it missing it, or how is this explanation?
Yeah, I don't know. I mean, I made this, so it's my understanding. So I hope that works.
Yeah, get the word out.
Yeah, but well, we can actually see a different situation. It's nice. It's nice animated, right? So if we have things running like that, we have big job like that, you know, sometimes the scheduler would do backfilling because I can see, you know, that job use a lot of nodes, but it actually doesn't last for that long. So it's fine for the 2 other jobs just waiting for a little bit longer to finish that large job. So that things can happen. Actually, Frontera prefers large job like that too. Okay. So there are different resource management policies, right? So, sometimes you end up with a situation like that. You have like a long tail job that doesn't use a lot of nodes, but lasts for a long time. Then you will have a job that got stuck and there's nothing you can do about it. But if you have a job that comes up later, that can actually fit into the space, the scheduler will actually do that for you. So that the resources is actually not being wasted. And it can actually push back the already queued job by that. If it's not like pushing back for too much. The scheduler got to decide like how much to
Yeah, this is quite dynamic, so there is no unique way for making more efficient. It depends a lot on what kind of work therapy. Because this ones, you said that it's preferable, but for that specific configuration, you are very behind.
Yes. So the thing is, this is really just an animated way to show you how things work, not meaning that it's really how it works, right? I mean, in real world, the scheduler makes a lot of decisions based on the current stats and the already queued jobs. And also there are different policies, like we can assign certain user or certain projects higher priority, then, those jobs will actually get prioritized. Things like that happens. But basically, I'm just showing you the strategies the scheduler normally use. And it's always a mixture of all these, okay? Was there?
No, I had some question.
Oh.
So because scheduler is automatic algorithm, right?
Mm-hmm. Yeah, scheduler has its internal algorithm that makes such decision. And usually you can configure it. So each different HPC center will usually configure their scheduler slightly differently to prefer a certain type of jobs. But yeah, we don't really tell you how that is being configured. I don't even know actually. So there are some commands you can use. You can use the sinfo command to actually show to list the available queues. Okay, so usually there are different queues, right? So there's a development queues, mostly for interactive kind of workload. There's a normal queue for normal jobs. There's a small queue for smaller jobs. There's a large queue for large jobs. And these are all configured by different centers. So this is the queues available on Frontera. But in your institutional HPC resource, there will be something different. But the command works the same if they're using Slurm. Attack, you can also use the queue limit command to actually look at what the limits of these different queues are. For example, like the development queues, you can use up to 40 nodes. For the normal queues, you need to be at least 3 nodes, right? Otherwise, you need to use a small queue, which is only for 1 or 2 nodes. Things like that. There's also like a maximum wall time limit that you can request. So sbatch is the command to submit the job. Sq is the way to check the queued jobs. Scancel is the command to cancel the existing queued jobs or running jobs. This is what a typical job script look like. Okay, you need to specify, the number of tasks, the number of nodes you'll be running, the queue you're submitting to, the wall clock time needed for this job, and of course your command. Okay. We also have the IDEF tool to help you initialize an interactive development session, which I hope will be the one that we will be trying out in 5 minutes. So you can just do IDEF. You can specify the queues, number of nodes, whatsoever, just like inside the job script. Attack is a little bit special that we don't do MPI run. We always use IB run. It's a wrapper around the MPI run command to help you better optimize the use of the network. But other than that, it's just basically a MPI run command. Okay. Yeah, that's not important. Containers. Okay. Let me see. Actually, okay, yeah, that's a hands-on session, finally. So let's try to run a container on Frontera right now. Also, just a way for you to try things out on Frontera. So if you SSH with your username at frontera.factory.texas.edu, you get access to the machine. You could run the module command, see what's there. You need to load the container module. You need to go to Scratch. Remember, right? We are just going to use the Scratch space. Okay. file system. And let me know if there's any questions. But let me go through all the steps first. Then I just let you work on it, and we naturally end the session. Okay, sounds good. We have like 15 minutes anyway. Yeah. So basically, once you get.
Raise your hand if you're not watching a chair.
Do that first.
Yeah, token is actually the MFA thing.
For those of you that already logged in, and if you're an instructor, please follow. Yeah, because like MFA,
so okay, the MFA thing. So sometimes some people actually came to me saying that they cannot pair the MFA. There are two different situations that will happen. First thing is you might had an account before, but you have not used it for a long time, so you get deactivated. And if that's the case, you need to submit a ticket, get your account reactivated. Okay, that's something. There's nothing we can do about it. The second, let me finish. The second issue is if you are from a country of concern defined by the US, your account will need to go through a manual verification process. That's not going to happen automatically. Oh, there's a third case, which is you need to use your institutional email to apply for an account. Otherwise, your account will not be verified automatically. Okay. Yes. Yeah, I need to add you to the project.
Yeah, so like, yeah, I don't know if that's right, but it's actually Google like but okay, you're trying to
Adding 50 accounts is crazy. Yeah, but there's no way to scriptize this. Oh, gosh. Not too late. But how to set it up though?
That's for weekend.
Yeah.
This doesn't specifically for the password. Ah.
Yeah. Yeah.
Is it one of them?
But yeah. Okay, so that might be
Yeah. Okay, next we can from now on. Yes, we can work around. Because they should hear this perfect.
So, for the in-person folks, please send me your username on Slack. And I can add you to a project. Otherwise, you won't be able to log in. For the online folks, we don't have resource for you. So if you have access to Coursera, that would be nice. If you don't, that's too much. Yeah. And if you have changed your password recently, it will actually take a few minutes to get updated. If you use your password may not work. Okay.
You only want you only want to use your name.
Did you? Yeah, then I need to add you. And right.
Thank you.
Yeah.
And for those that just add to the application, you may not be able to log in either, because it takes a while.
This is turned on. So that would look like. We have voila.
Great.
Okay. So you press on.
I'm done here anyway.
Yeah. Okay, so
Yeah.
let's play first. We can leave one in the. Muy bien.
On the online types and stuff.
We can't give them access to Frontier anyway.
From now on, do they need to?
Yeah, it's probably gonna be picked up by that Mac anyway. Yeah.
From now on, we just go around.
Yeah, that would be great.
Everyone on Zoom, they're trying to log into Frontera, and I found lots of microphones. So you will be able to hear. And for those who stick around, we should have created a cloud account for you. And so please stay on. I think we'll start in about 10 minutes, 5-10 minutes. We cannot provide Frontera accounts for the online attendees for security.
Yeah, no. Well, I think I only have a 29. Oh, we definitely haven't done your original yet. I didn't know. Yeah, yeah, yeah. You told me like that. Yeah. Someone goes to
Hello? Does it work? Hello?
I think it's your,
Maybe this one? Hello?
yeah, probably you need to put the sound from the computer because it's muted on the computer.
What is
So
it?
the sound from the computer, it's muted, and probably the sound is going from the computer to your home.
Oh, is it?
So there is no volume glitch. You have to put some sound. Everybody.
No, it's not muted. No, it works. Before Marine starts, if you still have issues logging into tag Frontera, come to me after today's session, okay? I mean, I only added like 29 persons, which is not anything near the 50 that should be at. So make sure to come to me if you don't have access, okay?
Thank you very much. All right, I think we'll get started. It's too loud, but they can hear better. All right, everybody knows you from class. So now we're gonna do the second piece of the onboarding process today, which is going to show you how to get on the cloud. And then we'll move on to tomorrow. So there is a lot of infrastructure building. Again, same for Ian, AI is good at making arts that finally look cool on our talks. Is this not gonna work? Okay. So what I'm going to show you, there's not gonna be any, is something that fails like this. We're going to show you today, briefly introduce what the cloud is. We have a much more extensive lecture on our YouTube channel. So this is going to be a summary and a practical knowledge about how to pay for the cloud, what a cloud instance is and whatnot. Because I get all of these questions of how much is this going to cost? So what the cloud is unlike HPC, it is still a computer center. But unlike the HPC system you saw, it is one where all of the hardware is not as tightly connected as what, for instance, Frontera is. So you can imagine all of these nodes similar to Frontera, more diverse, but distributed and not as connected. That means you cannot do HPC really on the cloud. The cloud will say, do you have HPC power? I'll show you why, but it's definitely not the 8,000 nodes that Frontera will give you. So they're still computer centers. They're physical computers. Microsoft, Amazon, all that do that, host them. These are no battery. But they what they provide and what we use them for observational seismology is their compute that is called a virtual machine, and their storage, which is set up as an object storage. their compute, and I'll put all the jargon out there so you get to know it. This virtual machine is an abstraction of hardware. You can fine-tune the CPUs, the memory, the local storage. You create your mini computer that you want to work on. They are stored, or they are accessible via the Elastic Compute EC2 system. And if you go on the web and you try to look for the type of instances, there are nodes, but instances for the cloud. Node is for HPC. You will notice that they have different purpose. They're very diverse. There's many different types of virtual machines. They're set up for different needs. You can customize so much that one may feel a bit lost in the options that you may have for compute. And so I just wanted to give a few examples. This one is called a storage optimized instance, the IM4GN. It's powered with a Graviton 2 processor. I have no clue what this is. It's good for, what does it say? It does 30 terabytes of SSDs. So if you actually know what a solid state drive and you do it Tensio, this is your friend. 30 terabytes of SSD attached to your instance. This is good. They have 60% lower IO latency than most other, and blah, blah, blah. And you can control, if you wish, the type of instance. So you can do a IM4GN large, which has 2 vCPUs, 8 gigs of memory, and what do they have? A terabyte about of SSDs. Their network bandwidth, you can see it's 25 gigs per second. This is much lower than in between nodes on an HPC center that can get more like to 400. This is 2500 gigs per second. And the bandwidth maybe for S3 is up to 10 gigs per second. And then you can actually customize it to go up to the 16x large, where you can get 64 vCPUs, more memory, more storage. Now the price tag matter. Here you're paying, 18 cents per hour for the small one versus paying $5, $6 per hour for the big one. This is where the variability comes. Bigger machine, more expensive. Smaller machine, cheaper. It's very simple. I'll show you a few other examples. The one that we tend to use a lot in our tutorials is the Ts, the T2s. These are the normal general purpose ones. They're used for small testing, microservices, whatnot. They're super cheap. They can be T2 Nano, I think it's free. The micro is for cost. You have 1 vCPU, it's tiny. And they are at $0.0058 per hour. And then the most expensive one, which has 8 vCPUs, T2X, 2X large, it has more memory, more vCPUs, and it's 30 cents per hour. So maybe by the end of this hour, all together, maybe all online 50 people will spend $20 at most in 1 hour. So actually for testing, it's actually very affordable. They're small. And you see when chip is small, this is completely orthogonal to big simulation. What we're going to try and do is very small code, very small deployment, because that's where the cheapest instances are. If you care about GPUs will show you some experiments, but you can use very fancy gear on these machines. If you check these ones, these called accelerated computing, the P5, they have 8 NVIDIA H100 Tensor Core GPUs. Nobody can afford this in an institution. They're like the best gear you can get. They have lots of vCPUs, 192, 8 GPUs just for you. We have a fancy machine at UW. It's got 4 A100s, and I'm so proud of it. This is nothing compared to this, right? They also have very tightly connected GPUs, so you can pass data in and out. $100 per hour. So expensive, so nice and fancy. What they do say, though, this is used for good machine learning training, like big models that you want to train. And apparently they have already spotted seismic analysis as part of their use case. I don't know who actually used that. but probably not a state school. But it's interesting that it noticed that this high performance computing is suitable for seismology. Another one that you may think is HPC-like, that I wanted to see, can we do wave simulation on the cloud? What is their HPC instance? You'll probably laugh because it's so small for you. It's if somebody can accept people on Zoom on my behalf, that would be great. It's their HPC 7A, for instance. I think these are a bigger one in terms of physical cores, 192. They have 700 gigs of memory. That's pretty good. And good bandwidth, 300 gigs per second, $7 an hour. So if you calculate how long it takes you to run a wavefield simulation, you always have to account for a smaller machine and how much it would cost per hour. So that's kind of the calculation we do in cloud computing. We try to see how much it will cost. Super cheap small instances, or would I actually invest in a big instance for training a model that would take 3 hours? And so it's very dynamic and it's not really comfortable for a lot of our developments. So we actually would rather develop locally and then deploy them maybe on the cloud. A lot of these prices are called on-demand price. So they are what you pay if you have complete priority on launching these jobs. But it turns out that we can actually use what we call a spot instance that will be 10% of that price. So you can still be smart in how you would use this instance or basically specify what they are. Spot is basically the unused instance that is available. If you remember Ian's scheduling cartoon with a little bit of holes in the scheduling, right? You can be on the lower priority and use spot that will fill the holes in what's available in the machine. So you may have an issue. Yeah.
Can I ask about like the decision of the money, basically? Like
Yeah.
sometimes it's more useful maybe to use a smaller computer, and like the process is gonna take more time. I mean, I wonder like if it always go bigger is the go big and that's the best always, or I mean, I know the results are limited, but I don't know what how you can optimize the money too.
Yeah, so here I actually see this as almost unlimited for seismological use case. There's just so much of it. There's so much storage that I feel unlimited there. What I think is important is, are we in a hurry? Like, do we need to do this quickly? Often, unless we're on a seismic network that actually issue early warning, no, right? I'm looking at past data. I'm patient. It takes much longer to write a code, than running this. So often I feel like it's okay to wait. And then the second, for the price and the usage, we have our own Linux machines and various kinds in a group, and they tend to be more or less used. But if you work in a spike, if you have a lot of time with unused resource in your group, this is when maybe deploying on the cloud might be useful because you're only using for when you need. And the other aspect, of course, is where is your data? And if the data is on the cloud, you don't necessarily want to download for months. Who's downloaded data for months in the past? Yeah, 4 months, 6 months sometimes, right? Now, when data is there, you process there, and the data and the throughput is fast. So these are the considerations. I think by the end of the week, you'll have a good sense for when to use it and what not. Okay, I'll show you. So today we're just gonna do access. But on Thursday and Friday, we'll talk about big computing. So I'll put some jargon here. The logos on the top right is this EC2 logo. The one in the middle, you've probably seen that before. It's called Kubernetes. You probably heard of Kubernetes before. It's a container orchestration. We love containers in this group. And so there you could orchestrate and schedule everything to automate the deployment. I think automation is a big word. I think Kubernetes actually are very hands-on. You have to understand the backend. You have to understand how to orchestrate all your containers and which machine. But it's one way, if you have a good IT staff, it's a one way to get your scaling going. What we'll be teaching is called AWS Batch, and that is the fully managed service. We're going to start with containers. We'll say up to how many VCPs do we want in one memory, and it will figure out what instances you need. We don't have to control it because honestly, we don't really care. So what batch does, which is this logo here, is it will pull from containers and orchestrates the cluster for you without you choosing much beside the maximum number of vCPUs and the memory. And so batch will, it's like Slurm in some ways, but for cloud, if that makes sense. Kubernetes, it's like this intermediate between you figuring out how Slurm works and making it work. So Kubernetes are a versatile platform because you can really customize everything, but we're not cloud engineers. We're scientists. We want to do science. So we recommend going through AWS Batch because that's tailored toward efficiently running your workflows. A little bit more on pricing. This was compute storage. Storage is expensive on AWS. So you don't want to pay for storage. It's using this object storage system, which is extremely resilient with high throughput and many queries at once. A single object, which is equivalent to a file or chunk of data stored on an S3, can be queried up to 5,000 times per second. So it's really good. It likes small mini seed files, like what we're used to in big data seismology. Lots of mini seed files that we can query 5,000 times a second. So you can imagine that in our compute, we're going to have many tiny computers, and we're going to query this S3 bucket. We don't care how many instances will be running at once, because we know that even if one file gets pinged, 3,000 times a second, we'll be fine. Because this is the massive throughput. It's really expensive to store, so we don't recommend that for any researcher, period, because I paid that. It was silly expenditures, but we learned by experience. The S3, I think it's like simple storage system, S3, for AWS. The standard rates are about 50 terabytes is $1,000 a month. Now, uploading on S3, that amount, it could cost to download the data or upload to S3, maybe $100, $200 to upload 50 terabytes on S3. So now you're thinking, okay, my compute is much cheaper than my storage, right? And so it completely changes the game from, well, we can actually just recompute things, because even in terms of ecology, like thinking about the environmental cost, your compute is you're storing data, you're paying for a center, energy and cooling system and everything to retain your data accessible. But when you compute, you're doing the same CO2 footprint, but instead you're doing it for 3 hours versus you can retain your data for many hours, many days. So this is my paradigm, I guess, in cloud computing, is thinking that I don't need persistent data stored there except if EarthScope stores it. But the compute part will be good. You can also have an infrequent access for maybe more long-term storage, because let's face it, our data is not that valuable. We care about our earthquake data, but maybe we're the only ones. And so if it's infrequent access, a little bit more latency in querying, you can spend still $600 a month. So this is where we don't recommend storing data, paying for storage. There's a lot of concern about egress. Egress is the idea that you download data from S3 to your local. And people are concerned about this because the EarthScope data services has moved the data there and is going to move toward this cloud system. Now, the other data sets, so NCEDC data and SCEDC data, Northern Southern California, are already on S3. They have a contract with AWS. It's an open data set, meaning that everybody without authentication can query it. And so it's free to download. EarthScope may have a different service, and so that's why there's been some concern about egress. Now, if you go on the website, you can see that you are allowed to not pay any egress fees up to 100 gigs of data per month of download, which is not bad. You can just, schedule your jobs to a split over time, except for some countries. So it was data, you can transfer data from your laptop to S3 for free. You can always, if you're on EC2, always get data from your local region storage. We can talk about what the region is for free. And so there's still a lot of benefits that you could waste money by downloading data, but you would have to be very inefficient. Also, at UW, apparently, we have a contract with AWS. We don't pay anything. So you can always VPN to a thing and download. I'm kidding. Okay, egress fees. It's free up to 100 gigs per month. It's always free to go from EC2 to S3 within the same region. It's free to upload to S3, and then you can have some contracts, so it's not as bad as people fear. Now, who pays for compute? Yay. Usually you have your own account, you pay with your own credit card. So that makes all researchers uncomfortable because now you see the bill of how much you're computing. Or you can write a cloud bank proposal to the NSF. Cloud bank is actually supporting this cloud credit that you're on. It's an NSF project to distribute cloud credit from IBM and Google and Microsoft and AWS if you have a grant from a specific set of solicitation to NSF and send you the recommendation. The link is here. So depending if you're doing I don't think geophysics is part of that list, but you can actually request cloud credit through Cloud Bank. Your institution may actually support you. We're right next to Microsoft, so we always get free Microsoft credits. But maybe your institution has contracts as well. And maybe some of the national archives will be, like EarthScope, will be providing some free credits in the form of a simple Jupyter Hub. Nothing to do massive batch processing, but still something that is good for exploring. All right. I wanted to have a quick note on abstraction of the cloud. We're debunking the cloud here. We are debunking it by learning a little bit the backend and trying to make it easy for all of you to access it. So we had to do a lot of learning, like especially over there, that room, and Quanfu as well. We just had to learn a lot, and it was just a lot of cloud engineering and learning how it works. But there are ways that you can completely abstract the cloud. It's called an infrastructure as a service. And it's very appealing. One of them is Coiled, and Coiled is very nice. If you just do Python, it's a way that it will look at your local Conda environment and then mask it, learn the dependencies, and map that onto an EC2 instance. And you're still learning you're still coding locally. So it's very nice. The one thing you don't see then is how performant is your code? Are you wasting resources? Are you inefficient somewhere? It's just mapping everything to make it look very easily, which I think we would recommend if your code is cloud optimized. So that's pretty nice. But we decided to understand how the cloud works, so hang with us. Okay, in that exploration, we'll show you one of these two pathways. We are exploring what cloud workflow will look like. Sounds easy, right? So if you look at this, you're like, oh my God, what did they have to do to get there? So we decided on two different types of workflows. They're all very AWS centric, but they're very similar on Azure. We have a paper on that. And so in big data seismology, we have the type of workflows that will cross-correlate a ton of data and then spit out this cross-correlation function. So we actually tend to amplify the data products by saving all of our intermediate data being seismograms. So we tend to do massive data throughput because we ingest 100 terabytes and we might spit 100 terabytes. Ugly. So what we do is we go in this way. We read data from S3. We cross-correlate, we do some stacking, you'll do some NumPy. This is Friday morning on batch, super exciting. But we spit all the data on S3 that you see here. And this is because it's 100 terabyte. It's gonna be a lot. And yeah, you don't wanna do a database for this, right? So it's big storage. And then we'll re-aggregate the data. Maybe we'll do some tomography or ambient monitoring or whatnot, which you can do on a Jupyter Hub or something like that. And then you delete your S3 bucket and just put stuff in your database that is readable. The other workflow is earthquake seismology, where you're extracting features like phase peaks, even types, you name it, like STLTA triggers or whatnot, which we'll try. In this case, we'll read a lot of data, but we only output just a small amount, maybe up to a gig of phase peak of cross correlation. That can be held into memory for a database. So there we recommend using a MongoDB database, and you saw Ian and Gary are fans of MongoDB. This is why we went this way. It's working very well. And so we're designing this database that hosts these small, phase peaks, small data. I call that small data. You can still have millions of phase peaks, but they're like 1 gig of storage. And then you can reaggregate the data by saying, I will use these peaks to locate the earthquake. This is the multi-station reaggregation, which can again look on batch or whatnot, and then re-output there. So this is a lot of trial and error. And I'm glad you may not have to do this part because that was interesting. Okay, so we're gonna soon get to it. The resources available, Amazon Web Services, Microsoft Azure, Google Cloud also does it. You can have something like super easy, ready, built Jupyter Access, or what we'll be doing is you can start from scratch and build your own system by pulling containers on empty instances. Pros and cons, almost infinitely scalable. It is much better than any Linux environment we have built in at the UW for our geophysics group. So we can really think big. Okay, maybe not as big as Frontera, but big for big data. We often just work out of our laptops on the beach. I'm kidding. The computational resources can be inexpensive when used wisely and or deployed wisely. And then it's really limited commitments. An example, we created, or you created automatically all of your accounts, maybe 100 accounts. And then by the end of the workshop, no more accounts. Okay, you can build and out accounts just like this. It's very convenient. It's also ephemeral, which can be a little bit scary. But we are sharing this, the SCOPED is sharing this resource with you to try and test the cloud for a week. And the cons, the lot of learning curve, big steep learning curve for a group. I'm excited to do science one day. Like I felt like with the past 2 years, we just built software. We're getting there. And maybe, AWS is a proprietary. It's not really it's not a simple Linux system. And storage is very expensive. No more lecture. Let's get started. So you has put something on Slack about accessing your cloud account, which comes with the URL that you see here. And as you start logging in, please use the email address that you use for registration. And especially for the Zoom participant, use the Zoom address that you use for registering. And then you'll be using a temporary password, scope 2024 at UW, no space. And then you'll be resetting it. And then we'll get going. Let's see. All right, so what does it look like? Do you want to come? If you want. Yeah? You're amazing.
I probably need to share my screen because I'm currently on Zoom.
Let me do it.
Because I'm participating.
Yeah. I lost Zoom. Am I still screen sharing?
Yeah.
Do you see?
But I need to run the screen.
No, I just can't see.
On your laptop now.
Did I zoom out?
No, you're still here.
Okay, I'm lost.
Oh, you don't see your.
Yep. A Zoom?
Windows?
Probably because you're screen sharing now.
Yeah, no, but I don't know where it is. I lost Zoom. Oh no.
Yeah, at the same time, please try to log in with the email address.
Voila. It's easier to go this way.
Oh. So I need to share my.
I'll find you. Yeah, you can. And your co-host.
Yeah.
And I'll mute.
And I'll mute. Sorry.
And I'll walk around.
That's good. Okay. Oh, why it's not showing anything here? Okay, sounds good. Okay, hi, everyone. So this is going to be the first hands-on session for the cloud computing, and we just send you the login URL. But if you don't have that, I'm going to send this link in the channels. So after click it, you will find there's a note for workshop participants, and there's a sign-in address here. So what I'm going to do is to log in with my participant account. If this is the first time you are logging into this AWS account, please use scope 2024 at UW, no space or lowercase for a temporary password. And for your first login session, it will ask you to reset a strong password. Yes, I'm sharing the screen, I think. Oh, really? Sorry, apology. Does that look good? Okay, sounds good. So this is going to be the AWS Web Console that takes control of all the service that AWS is providing. So there are several commonly used service like EC2. I'm listing here. It's a service I recently used. EC2 called Elastic Computing Cloud. Basically, launch all of your virtual machines, set up the computing nodes. IAM, it's a user management. The cloud is sort of different from your Linux account that you just set up with users, user groups. The permissions on cloud is kind of tricky compared to your local environment. S3, as Marine mentioned, is a simple storage service that basically you can put all of your files on the cloud. And the batch, which we are going to go through on Thursdays, is kind of like launching parallel jobs, a big job that you can have hundreds of CPUs, hundreds of gigabytes of memories, is usually for massive parallelization. And what we are going to do in this small hands-on session is that we are going to launch a small instance specifically belongs to you that no one else has access to, and we're going to run a Jupyter notebook and access some data from the Southern California Earthquake Data Center. So if you don't have the EC2 logo on your console home, please search for EC2 in the search box here, and then what we are looking for is here is a EC2 service, and we are going to launch the instance. It's highlighted here. Basically, it means you are going to launch the virtual machines for you. In this panel, there are going to be several fields that you need to specify. There are tons of variables you can specify for your virtual machine. The names, most importantly, the operating systems. You can do Linux, you can do Windows, you can do Mac, and there's some of the other operation systems I haven't ever used before. I'll just go through this field and launch my own one. So first, I'm going to give my instance a name. For example, I'm going to type test. So this is going to be a name that tells you that, hey, this is your instance. Don't access others' instance for. Okay. Yeah, so remember the name of your instance. Uh-huh. Oh, yeah, yes. Sorry. I forgot to mention. So cloud is separated by regions. So we have 4 different geographical regions, and these data are located in different regions all around the world. And for the data we are going to access at SCDC, they are located in the US West 2 region, which we highly recommend you to move your service to. In order to do that, on your top right panel, there's a Dropbox here. And we recommend everyone to specify US West, Oregon. This is important to have better access experience with the SCDC data.
It's a physical warehouse.
Yeah.
So you want to use the computer in warehouse and not use internet to go to.
There are generally more latencies if you want to visit data using a machine here, but the data is on the East Coast, the US, or in Europe, something. Yeah, it,
how large the data set is, but like.
yeah, usually cloud are optimized for the data and the resources located within the same region. Visiting the data outside of your region usually means more cost, more latencies, and potentially failures or something. Yeah. Yeah. Okay, so make sure you are in US West to Oregon State. Not here, but virtually. And we're keep going for that. And for your operating system, we're just using the default one, the Amazon Linux. So it's a Linux machine, and you can have the typical command line to access to it. And so this field, instance type, it is very important. So on the cloud, on the HPC system, you submit a job and specify how many nodes you want, how many CPUs, memories you may want. And on the cloud, this is specified by the instance type. When choosing an instance type, it means that you specify how many CPUs, memories, and also potentially the price of your instance. So the better instance, you're paying for more at higher rate. And we kind of have tons of instance type in this list, but for this hands-on session, it's really computation minimal. So I would recommend people using like a T2 large. That should be enough with 2 virtual CPUs 8 gigs of memory, and you can also see how much it costs. Like here, it costs 0.09 or $0.1 per hour, and it can be even lower when you're using the spot instance. So I'm going to choose T2 large, but you can also do a bigger one, like X2 large if you keep moving down. Never mind, S2 large. So the key pair is something that you will need if you want to SSH to log into your account. So you cannot specify your password here. The AWS use a credential file downloaded locally to identify that someone logging into your instance is actually yourself, not someone else. But we're going to do some tricky things, but and going to skip this session for the key pair. Just omit it. We're not going to SSH into your instance. So I'm just skip this part. Yeah, we had some problems during the SSA workshops that some Windows users have some conflict with key files and they cannot easily connect to the instance. So later we find a way to just bypass this step. So the network settings, basically it tells the instance which part of the port are allowed for connection, SSH for port 22, HTTP 80, HTTPS 443. These are default enabled by network setting. So we pre-configured a network setting. So you can choose that by selecting the existing security group. And then in the Dropbox, select the default one. So this is going to this is a network setting that we have already pre-configured for all the participants. Okay, and lastly, the storage. So we're not going to share storage for everyone, and you have the choice to specify how many drives you want on your instance. For today's session, I would recommend 20 gigs. Simply increase this number to 20. Just as easy. You don't need to configure your reformat it or something. After all these steps, we should be ready to launch our instance. So these are all the configurations required for the instance. I'm going to, I'll just skip it. Don't worry about it. Yeah, for the key pair login, just leave it blanket. It says required, but it's not required. Yeah, that's a AWS problem. It says required. And when you launch the instance, it will ask you, do you really want to skip this part? Because once you create it, you cannot log in from your laptop without a key pair anymore. But I insist on this. I'll just proceed without a key pair. Okay. Success means that there's a virtual machine physically running in Oregon, in the state of Oregon, that you will have access to. At this time, I will show you how many of us are launching the instances at this time. And as mentioned, it's a shared environment. So don't try to terminate other people's instance because it's kind of shared. Okay, 34 people right now. More people are launching their instance. And on this panel, I can see that all of the configurations each of you are using. For example, when click one of the instance, I can see that there's a public IPv4 address, public DNS address, and all of the parameters you are using for that virtual machine. Yeah, everyone can see it. You can try to see others, but don't try to terminate them.
let's say one people try to cloud computing and I have no idea what to set up my computer. So probably if I'm curious, I can go and check your architecture because you have a lot of experience.
Yeah, I think that's a good practice actually. This there are a lot of tricky things in computing, and it's really necessary to have a good tutorial and to follow up, especially with all of the parameters to configure. Yeah, but yeah, practice is also important. Okay, it's 41. So I'm going to try to connect to my instance. So remember the name of your instance. So I'm going to type, this is my name and test. So after figuring out someone, that's all I have. So someone is not mimicking the name of the instance. I can click it. There's a highlight here. And connect. There's a button here called connect. It tells you how you can connect your instance. Previously, we're using the SSH client as mentioned, which requires you to have a key file. But this time, we're going to use the EC2 instance connect button and simply connect it. It will be a pop-up, and there will be a browser new tab and connect to your instance directly. This is typically how you will typically see when you successfully SSH'd into an instance. Anyone seeing this? Hands up. Cool. Yep. Any questions? Any questions so far?
Do
I kind of
I don't know, it's more like peaceful. Then you can go.
I kind of use this one every time I log into my shell terminal. I don't really check what it's saying, but it's just a just a fun thing. All good?
Are you all good?
Cool. So after logging into this instance, we'll find that there's really nothing here. It's just empty. And one of the biggest problem when launching the scientific computing code is that you have to find a way to configure your environment, install Conda, install Python, and all sort of things, which can be really, really tedious and time consuming. Sometimes it get failed. So what we are going to do is to use the techniques we mentioned this early today is a container. So we pre-configured a container that with all of the required software installed. And to do that, I'm going to ask you to use the link I just sent in the channel. So there are a code cell. You can simply copy it, paste it in the terminal that basically install everything, install the Docker on your instance. So there's still one critical step that you need to install Dockers in order to run Docker container. Anyone finding this on the HPS book? I'm also going to copy paste it in the channel and paste it here. And the next step we'll be doing is to pull the image that contains all the softwares. What I'm going to do is to copy paste the same command here. So you will see that this instance is downloading all the Docker container, the images from the image pool. take some time usually. Put in your image. Yeah. That's good. After this step, the Docker image has been downloaded locally to the EC2 instance, and we will going to launch the the Docker container. So there's a third code block. Going to run it here, and it doesn't really gives you anything here, but it's actually already launching a Jupyter node Jupyter lab on the backend that we can get access to. So after running this code, okay, I'm gonna pause a little bit and wait for people a little bit. Just give a quick introduction about this command. So it tells you that we're running this Docker image with Jupyter Lab installed, and the rest are all the arguments for the Jupyter Lab. Questions? Yep. Oh, okay. So so the next question is where the Jupyter Lab is actually running. So the way we configure this is that it's running at port 80, which is the HTTP port. So we can go back to the instance summary. There's a public IPv4 DNS. We can simply copy that, paste it in the browser, and that's where the Jupyter Lab is actually running. Questions? Something look like this: EC2 or something, and US West to .compute .amazon AWS. Questions? Seeing the login page. So it's asking for a spoiler. Password is simply scoped. Questions? Might help in the presentation. Oh. While our TA teams are helping, Yeah, so for this container, you'll find that it has every Python packages installed, pre-configured already. So you can, if you have a tutorial for your tools you build for your research, that you can save it here, freeze it here. For example, if you click the Seismic Cloud, there are several notebooks that we prepared for this session, which I believe we may not have enough time for that. But if you click that, you'll find these are pre-configured working materials that you can play with. So no more paying for environment configurations. It's kind of the spirit for the Docker container.
Next week, we have access to resources.
Exactly. So the Docker image is saving on the GitHub. So as long as you have a Docker installed on your local computer, you can always connect to it. Okay. Yeah. So it doesn't matter where you are running that.
Okay. So
Yes. And another important thing about this cloud is that SCDC data are public available, meaning that you don't need a AWS account to access it. So everyone can access it on their cell phone, on their laptop, on their lab Mac or something. So yeah, I may go through the first part of this, just the first half part of this notebook, and later we'll have the poster session. It's important to show you that how we can have a direct access to the S3 bucket. So I'm going to finish the earlier part of the book. Yeah, I'm not going to run the SCDs, the picking part. Yeah. So if you can follow me and run this notebook, we can go through, have a direct access to the SCDC data. So previously we are having the OpsPy client that you request data, get the waveform, specify the station, network, channel, and it's being loaded directly at the OpsPy string. So have you ever been curious about how SCDC saving their data as mini-seed file? So this notebook allows you to have a direct access. So cloud data are grouped by bucket. So for SCDC, they name their bucket name as SCDC-PDS. I guess the name means public data service. If you click around this cell, you'll find that this is how they group their raw data archive. You can find FDSN station XML file. There are some DAS datasets. There's continuous waveforms, earthquake catalogs, raw pics, and windowed waveform from the earthquake. And we can keep going. So these are folder-like structure. You can change the path. For that, you are getting deeper into the directory structure. For example, if I'm curious about the FDSN station XML file, so I change the path here, and I find that there's CI network, which are the major SDDC data, and there are some other they called all unauthoritative XML file. So I'll just go with CI. So these are all the station XML files available at SCDC. A lot.
This is the worst part actually of the storage.
And this is a similar case for the continuous waveform that we don't need to have the OpsPy client anymore. we still need to parse them with OpsPy. So you see there's a continuous waveforms. I'm going to go through this folder, this grouped by years. I'm going to have a 2024. And it's further grouped by year and day of year. And then this is a fundamental structure of the SCDC's data. Yeah, in order to read them, these are the next two cells I'm going to run. So import NoisePy, and I will have direct access to one of the miniseed file. So you'll find that it seems like you're having this file locally on your laptop. So you don't need to download it on your laptop, group it, structure it, and in a way that not only yourself but others can understand. So this is going to be the standard of the SCDC data center. A similar case will be with the XML file. It specifies a path, read it with OpsPy read inventory function, and you will have the station response metadata for this specific station. Questions, comments?
Yeah.
Yes. Yeah. One of the advantages is that you are running this code within the same region of that data. So the connection between the data center and your instance is tremendously fast, actually.
It's impressive.
Yeah. That's I think that will be the last code cell running for this session. But any questions about the EC2, about the S3, feel free to raise your hand. Yes, yeah. Yes.
Yeah.
Yeah. Oh, you cannot see that directly because on the left panel, this is what you have on your instance. But S3 is somewhere kind of centralized, and you only have access to it, but not here, not somewhere here.
So you have to do the write, string that write to see locally? Is that right?
Yeah, if you want to save it here, you can write it using OpsPy, but you have to load it in your memory first.
Like if I write like a Python script in the terminal, like the session is always open. I mean, I don't need to. I can close the browser. I can close the.
Yeah, you can.
Perfect ending of this session.
I'm going to.
Yeah.
I'm going to just close it. Yeah.
So, yeah.
Excuse me.
You can download like normal OpsPy get data. It's not satisfying.
But you're not getting the advantage of cloud computing in that case.
Oh, you can still paralyze the download. But then Iris will capture.
Yeah.
IP. But it's already there, so it's coming. Now let's talk about terminating an instance. And I've been always telling people, please terminate, terminate, terminate. It turns out that some PIs and I forgot to terminate our own instances. So lesson learned. It was not too bad because it was a cheap one. So let's walk through terminating.
Yeah. I'll just show the Jupyter Lab for the last time because I closed it and I go back to it and it's still here.
You close the browser, you're still running.
Okay.
Yeah.
Yeah.
But dangerous because if you forget about it for a month, that's the problem. That's the leaky month.
Yeah. For terminating, we can go back to the AWS Web Console, and there's an instance state that allows you to stop it, meaning that your memory is kind of freezed and you can restore it. You are not destructing it permanently. The same case for reboot, but for terminate, you are kind of losing everything inside of that. So I'm going to terminate that, meaning that the notebook I just run is kind of lost. But that's okay. Oh, yeah. No, you don't keep it.
Stop. There's some.
No, you don't pay for it.
There's no stop. There's no like local storage save.
You're asking for the pay. Yes. Oh yeah. You don't pay for the instance, but
Can you pay for the image?
no, not image. Kind of the. Yeah. But it's minimal compared to the instance. Very minimal.
Yeah. Yeah.
Very minimal.
Terminate.
Basically, that's the cost is for freezing your RAM because still take some space.
Everything goes away. But you have GitHub and a container, you're set.
I'm going to terminate it. But that's okay because we have containers, so everything can be relaunched with little cost.
April? No, you're not. Only if you launch an instance, you start paying. Run or store, or pay for a service. Logging in, it's free. Then you pay. Because it's a computer running. You've reserved a resource. And so you're paying for the resource. Yeah, it is kind of submitting a job that runs idle. Yes. There's a lot of similarities because you still log in to launch. If you launch at scale, then we have other services like Slurm. All right, so we're terminating and we can see who is not terminating.
That's fine.
Now we haven't found the automated terminating for the group, but for when you have a research group, managing this is we don't know how to automatically manage resources that are shared like this. And so somebody has to open and check who's running. So during this workshop, we're probably gonna kill things at night. Everything could be killed at night because you have admin permission for this. And then at the end of the workshop, everything will go again. Mm-hmm. Yeah, it will stop when it's done. Yeah. So for batch, yeah.
Yeah, you can set up a timeout for a different job, but this is only like launching a virtual machine. The AWS wouldn't want to kill your instance accidentally. It's kind of advanced other service provided by AWS.
For instance, there is an instance there is no name.
Yeah, it's okay. It's just a tag. As long as you know that instance is yours, it's totally fine. But you see the.
Yeah.
Oh, that's why you don't know who instances are, right? And you might accidentally terminate it. So that's like a practice. Cool.
All right. Yeah, that was great. Thank you so much, you. Taking all this. You need to go connect to the cloud. So you've got a VHPC and the cloud, it's a small private sign. You make back more, you set them, and MCQ, you deactivate. And right now, boosters. Okay, yeah, good day.
For those online, see you tomorrow.